Welcome to Sleep to Science. Tonight, we're diving into the hidden physics that make Earth the universe's most extraordinary accident. Look around at the flowing rivers, the air you're breathing, the comfortable temperature that lets you exist without a spacesuit. All of this feels perfectly normal. But what if that normalcy masks the most improbable cosmic coincidence ever discovered? After scanning thousands of distant worlds with billion-dollar telescopes, astronomers have made a discovery that should humble our entire species. We may be living on the only planet in the observable universe where liquid oceans dance freely across the surface. Tonight we'll trace the hidden nuclear reactor spinning beneath your feet that's been protecting life for 4.6 billion years straight. You'll discover how Earth's living crust moves in ways that no other planet has mastered. And we'll explore the gravitational partnership between Earth and our impossibly oversized moon. A cosmic accident so unlikely it borders on the mathematically impossible. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Space Telescope have been playing the ultimate cosmic treasure hunt. Armed with instruments worth billions, they've been scanning distant worlds for any trace of what we see every time we visit a beach. Liquid water flowing freely across a planetary surface. The results should make every human being stop and stare. Astronomers have discovered over 5,400 planets orbiting distant stars. After analyzing their atmospheres with obsessive precision and after decades of systematic searching, Earth remains the only confirmed world where vast liquid oceans cover the surface. Not one of the few, not rare but discoverable, the only one, period. This isn't because our technology lacks the power to spot others. The physics of maintaining liquid water on a planetary surface proves brutally unforgiving. Almost every world fails spectacularly. Think of it as the universe's cruelest obstacle course, designed specifically to eliminate liquid water at every possible opportunity. Too close to the parent star, welcome to Venus, a 900-degree hellscape where lead melts on the surface. Any water that ever existed bowled away into space billions of years ago. Too far from the star, meet Mars, a frozen wasteland where the atmosphere became so thin that liquid water can't exist anywhere. Only polar ice caps and underground permafrost remain. But here's what elevates Earth's achievement from merely rare to genuinely mind-blowing. Our planet hasn't just managed to maintain liquid water for some brief cosmic moment. Earth has been running this impossible balancing act flawlessly for over 4 billion years. Through asteroid bombardments that vaporized entire continents, through volcanic eruptions that blocked sunlight for decades, through ice ages and greenhouse periods that should have frozen or boiled our oceans completely, Earth operates like the universe's most sophisticated thermostat. When temperatures rise too much, increased evaporation creates more clouds. These clouds reflect sunlight back to space. When things get too cold, reduced cloud cover allows more solar heating to reach the surface. These feedback loops work with engineering precision. Among roughly 2 trillion galaxies, each containing hundreds of billions of stars, Earth appears to be the cosmos's only success story. We're not just rare. We might actually be unique. What if I told you that beneath your feet, something absolutely remarkable is happening right now? While Mars grew cold and geologically dead over 3 billion years ago, Earth maintains a nuclear powerhouse deep underground. This furnace has been operating continuously since our planet formed. Picture a reactor that's been burning nonstop for 4.6 billion years, never once shutting down, never once running out of fuel. This isn't leftover warmth slowly cooling from Earth's violent birth. This is active nuclear energy production happening every second. Deep within our planet's core, unstable atoms are splitting apart. Uranium, thorium, and potassium buried in Earth's interior break down constantly. They release heat equivalent to roughly 44,000 nuclear power plants running simultaneously. That's 44 trillion watts of continuous power generation every single day. Think about that scale for a moment. Our planet generates enough energy internally to power the entire United States for 4,000 years. From atomic decay alone, this nuclear fuel supply will keep flowing for over 5 billion more years. All this atomic energy drives Earth's most spectacular hidden machinery. The heat creates churning currents in a massive ocean of liquid iron. This ocean flows 2,900 kilometers beneath the surface. That's roughly the distance from New York to Los Angeles, but straight down into the planet. This molten metal sea moves in complex patterns. Earth's rotation and internal heat drive these patterns. The moving liquid metal creates electrical currents. These currents produce our planet's protective magnetic field through the same principles that power industrial dynamos. This magnetic shield extends 60,000 kilometers into space, an invisible fortress that deflects deadly solar radiation. Without it, that radiation would strip away our atmosphere within a few million years. But the nuclear engine powers something even grander. Hot rock rises from depths greater than the distance between Chicago and Denver. It spreads horizontally beneath continents and ocean floors. Then it sinks back down in circulation cycles lasting hundreds of millions of years. These slow-motion currents drive the movement of Earth's crustal plates. Every earthquake, every volcanic eruption, every mountain range, all powered by atomic decay deep within the planet. Mars cooled so thoroughly its core became partially solid. This ended the magnetic field that once protected its atmosphere. Venus may still have some internal heat, but lost the surface recycling that keeps a planet geologically young. Earth alone sustains this triple combination: continuous atomic energy, thermal circulation, magnetic field generation. We're riding on a cosmic powerhouse that's been operating at full capacity for nearly 1/3 of the universe's entire existence. And it shows no signs of slowing down. Close your eyes and try to sense the ground beneath your feet. Feels pretty solid and motionless, right? Here's something that might change how you think about solid ground forever. Right now, as you sit there, you're riding on a massive rocky plate. This plate slides across Earth's surface at roughly the same speed your fingernails grow. That doesn't sound impressive until you realize what makes this absolutely extraordinary in cosmic terms. Among all the rocky planets we've discovered, Earth possesses something vanishingly rare throughout the universe: a surface that actually moves. Venus displays a crust so thick and rigid it locked into place billions of years ago. Mars cooled so quickly its surface became frozen in geological time. Earth somehow learned to dance. Our planet's outer shell consists of massive rocky plates floating on partially molten rock deep underground. These plates slide, collide, and separate in endless geological choreography. Picture 7 major dancers and dozens of smaller ones, each between 5 and 100 kilometers thick, all gliding across a stage the size of a planet. The Pacific Plate slides northwest toward Asia at 7 centimeters per year. The Indian Plate continues its collision with Eurasia. This pushes the Himalayas higher each year. The underwater mountain range down the middle of the Atlantic spreads the ocean floor. It gradually separates the Americas from Europe and Africa. But why does Earth dance when no other planet learned the steps? The secret lies in our planet's perfect recipe of internal heat and surface conditions. Too much internal energy and the crust becomes so soft it can't form rigid plates. Too little heat and everything locks up permanently. Earth hit the sweet spot where the crust stays just rigid enough to form discrete plates. Yet the underlying rock remains just soft enough to allow movement. This constant surface recycling creates geological activity that reshapes our world across deep time. At underwater mountain ranges, plates separate. New ocean floor forms as molten rock wells up from the depths. At zones where ocean floor plunges back into the planet's interior, seafloor gets recycled back into the mantle. This seafloor can be over 200 million years old. Every earthquake represents this ongoing dance. Every volcanic eruption marks places where the dance becomes most energetic. Every mountain range shows where plates have collided in slow-motion crashes lasting millions of years. Among thousands of exoplanets surveyed by our most advanced telescopes, astronomers have detected no evidence of active plate movement anywhere else. Earth alone mastered the geological bolide that has been reshaping its surface for over 3 billion years. We're witnessing what may be the universe's only performance of planetary plate tectonics. Sometimes the rarest things happen right beneath our feet. Right this moment, you're under attack by invisible particles racing toward Earth at millions of miles per hour. The sun hurls a constant stream of charged particles called solar wind in our direction. Distant exploding stars add cosmic rays traveling at nearly the speed of light. This invisible bombardment carries enough energy to strip away our atmosphere and sterilize our planet's surface within a few million years. You can't see this cosmic assault, you can't feel it, but it never stops. 24 hours a day, 7 days a week, for the past 4.6 billion years. So why aren't we dead? How does Earth defend itself against this relentless cosmic gunfire that would turn our world into a lifeless rock? The answer lies in the most remarkable defense system in the known solar system. An invisible magnetic shield that extends 60,000 kilometers into space. It surrounds our entire world like a protective bubble. Earth generates the solar system's most powerful planetary magnetic field. This magnetic fortress deflects the solar wind around our planet. It creates a protective zone called the magnetosphere. This zone channels deadly particles safely past us. When solar storms intensify, our magnetic field responds like a living shield. It automatically strengthens its defenses. It redirects the worst of the particle storm toward the polar regions. That redirection creates one of nature's most beautiful side effects. When the deflected particles finally interact with our upper atmosphere at the poles, they generate the dancing lights of the aurora. The northern and southern lights paint the polar skies in curtains of green, blue, and red. This magnetic protection operates through continuous motion deep within our planet. Remember that massive ocean of liquid iron churning 2,900 kilometers below the surface. That molten metal moves in complex patterns driven by Earth's rotation and internal heat. The flowing liquid iron acts exactly like the copper wires spinning inside an electrical generator. It creates the electrical currents that produce our magnetic field. This GDMO has been operating for over 3.5 billion years without interruption. No maintenance required. No fuel consumption except the radioactive decay that powers Earth's internal heat engine. The uniqueness becomes crystal clear when we examine our planetary neighbors. Mars lost its magnetic field billions of years ago. Solar wind has since stripped away most of its atmosphere. This left behind a thin, cold environment where liquid water can't exist. Venus never developed a strong magnetic field. Constant solar bombardment helped transform its atmosphere into a toxic greenhouse. Among all the rocky planets in our solar system, only Earth maintains the powerful, stable magnetic field necessary to deflect cosmic radiation. We live under a planetary defense system so sophisticated and reliable that it may be genuinely one of a kind in the entire galaxy. Take a deep breath. Go ahead, just breathe normally for a moment. What you just inhaled represents the universe's most remarkable atmospheric achievement. Nothing like it exists anywhere else in the known cosmos. This mixture took billions of years to perfect. That breath contained roughly 78% nitrogen and 21% oxygen, with trace amounts of other gases making up the difference. It might sound like arbitrary chemistry, but those percentages represent what may be the most fine-tuned recipe in the universe. Change those numbers by even a few percentage points, and complex life becomes impossible. Why does this specific mixture matter so much? Oxygen makes energetic life possible, but it's also dangerously reactive. Too little oxygen in complex animals cannot extract enough energy to power large bodies and active brains. Too much oxygen in the entire planet becomes a tinderbox. At 30% oxygen, forests would burn so aggressively that any spark would trigger planet-wide fires. Lightning storms would ignite continents. Even worse, pure oxygen becomes toxic to most life forms after a few hours. Nitrogen serves as the perfect diluting agent. It's chemically stable, so it doesn't react violently. But it also provides pressure that makes water stay liquid and helps oxygen behave safely. This creates what chemists call a buffered atmosphere, reactive enough to support energetic life, but stable enough to prevent atmospheric catastrophe. The 78-to-21 ratio hits the sweet spot where fire can exist but won't consume the world. It's where breathing can power complex organisms but won't poison them. Earth's atmosphere took over 2 billion years to reach this balance. Nitrogen was here from the beginning, released by volcanic outgassing during our planet's violent youth. But the oxygen that makes energetic life possible had to be manufactured by living organisms themselves. Around 2.5 billion years ago, tiny organisms called cyanobacteria started producing oxygen through photosynthesis. This triggered what scientists call the Great Oxidation Event. During this transition, Earth could have easily developed too much oxygen or too little. It could have become permanently frozen under methane haze or burned under excess oxygen. Thousands of things could have gone wrong during the 2 billion year atmospheric refinement process. Yet somehow our planet maintained the delicate chemical balance necessary to arrive at today's breathable mixture. We've now analyzed the atmospheres of thousands of exoplanets using our most advanced telescopes. We find worlds with thick hydrogen atmospheres, worlds with carbon dioxide-dominated atmospheres like Venus, worlds with almost no atmosphere at all like Mars. But nowhere have we detected the precise nitrogen-oxygen balance that makes Earth's atmosphere uniquely suitable for complex life. That breath you just took represents the culmination of a 4.6 billion year atmospheric experiment. It appears to have succeeded exactly once in the observable universe. Look up at the moon tonight and try to grasp what you're actually seeing. You're looking at one of the solar system's greatest anomalies, a companion so large that it rewrites the rules of what moons are supposed to be. Most planets have moons that are tiny compared to their parent world. Jupiter's largest moon, Ganymede, measures less than 1/26th of Jupiter's diameter. Saturn's biggest moon, Titan, comes in at roughly 1/22nd of Saturn's size. Even Pluto's largest moon, Charon, is only about 1/9 of Pluto's diameter. But our moon is massive. It's 1/4 of Earth's diameter. This makes it by far the largest satellite relative to its planet in the entire solar system. It's so big that some astronomers argue Earth and the Moon should be considered a double-planet system. This enormous companion creates effects that no other planet experiences. The Moon stabilizes Earth's rotation like a cosmic gyroscope. Without it, Earth's tilt would wobble chaotically over millions of years. Our planet could swing from near upright to dramatically sideways, like Mars. That would cause extreme climate shifts. Ice ages would come and go unpredictably. Deserts would migrate across continents. The stable seasons that complex life depends on might never have existed. The Moon also drives our ocean tides. It pulls on our water with gravitational force, creating the rhythmic rise and fall that shapes coastlines and powers entire ecosystems. Tidal pools, intertidal zones, and the mixing of ocean nutrients all depend on this gravitational dance. But here's what makes the Moon's existence so mind-bending. It shouldn't be there at all. The leading theory is called the giant impact hypothesis. Around 4.5 billion years ago, a Mars-sized object collided with the early Earth. The impact was so violent that it vaporized rock and hurled debris into orbit. That debris gradually coalesced into the Moon. This explains the Moon's composition. It's made of material similar to Earth's mantle, not captured space rock. It explains why the Moon has so little iron. Most of the iron sank into Earth's core during the impact. But the odds of this happening are astonishingly small. The impact had to occur at just the right angle. Too direct, and the two bodies would merge completely. Too glancing, and the impactor would ricochet away, leaving Earth without a moon. The impactor had to be the right size. Too small, and it would not eject enough material to form a large moon. Too large, and it could have destroyed Earth entirely or stripped away our atmosphere. The timing had to be perfect. This collision had to happen after Earth formed a solid crust, but before it stabilized completely. Too early, and Earth would have melted into chaos. Too late, and the debris escapes into space rather than forming a stable satellite. Among thousands of confirmed exoplanet systems, astronomers have found no clear evidence of another Earth-Moon-style pairing. Our planet, with its quarter-sized companion, appears to be genuinely unique. A cosmic accident so improbable that it may have happened only once in the observable universe. Earth sits exactly 93 million miles from our Sun. That number might sound arbitrary, like someone just picked a random distance and called it good. But this cosmic address represents the universe's most exclusive piece of real estate. A location so precisely calibrated that moving our planet just a few million miles in either direction would transform Earth from a garden paradise into a lifeless wasteland. Astronomers have given this special orbital zone a name that sounds like a children's story. The habitable zone, also called the Goldilocks zone. Just like Goldilocks found the porridge that was neither too hot nor too cold, Earth occupies the one orbital distance where temperatures stay just right. This cosmic sweet spot extends from about 85 million miles to roughly 110 million miles from our Sun. That might seem like a comfortable margin for error, but it's actually an incredibly narrow target when you consider the vast scale of our solar system. The entire habitable zone spans just 25 million miles. Our solar system stretches over 7 billion miles from the Sun to its outer edge. Here's where Earth's real estate gets truly remarkable. we don't just barely squeeze into this habitable zone. We sit almost dead center in the most stable part of it. Our orbital distance keeps global average temperatures around 59 degrees Fahrenheit, perfect for maintaining vast liquid oceans. It also prevents runaway greenhouse effects or global freezing. But what makes this positioning even more extraordinary becomes clear when we examine how fussy the universe is about planetary placement. Computer models show that if Earth formed just 5% closer to the Sun, our oceans would have boiled away within the first billion years. Surface temperatures would have climbed above 200 degrees Fahrenheit permanently. Move Earth just 5% farther out, and our planet would have frozen solid. Average global temperatures would hover around -50 degrees Fahrenheit. The water cycle would shut down completely. Our atmosphere would gradually condense and fall to the surface as snow. Among the thousands of exoplanets we've discovered, most orbit either too close to their stars or too far away to support liquid water. Finding planets in their star's habitable zone proves remarkably rare. Finding one positioned as perfectly as Earth appears to be virtually unprecedented. We won the cosmic lottery by landing in the universe's most exclusive neighborhood, and apparently we're the only residents anyone has found so far. Imagine you could grab our planet like a marble and move it around the solar system. Nudge Earth just 1% closer to the Sun, a tiny adjustment of less than 1,000,000 miles, and you'd trigger an atmospheric meltdown. This meltdown would make Earth uninhabitable within a few 100 million years. That 1% shift inward would increase solar heating by roughly 2%. Doesn't sound like much, does it? But that seemingly modest temperature bump would trigger what climate scientists call a runaway greenhouse effect. More heating means more water evaporation. More water vapor in the atmosphere means better heat trapping. Better heat trapping means even more heating. The cycle feeds on itself until oceans boil away completely. We know this scenario isn't hypothetical because we can see the end result orbiting next door. Venus sits just 67 million miles from the Sun. That's about 26 million miles closer than Earth. That extra proximity helped transform Venus into a hellscape. Surface temperatures around 900 degrees Fahrenheit. Atmospheric pressures 90 times greater than Earth's. Lead would melt on Venus's surface. The atmospheric pressure would crush a human body instantly. Now nudge Earth 1% farther from the Sun instead. This moves our planet just under 1,000,000 miles toward Mars's orbit. It reduces solar heating by roughly 2%. Again, doesn't sound dramatic, but that small decrease would gradually freeze Earth's water cycle. Less evaporation means fewer clouds. Fewer clouds means more heat escaping to space. More heat loss means lower global temperatures. Eventually, the oceans freeze and the atmosphere condenses. Mars demonstrates this frozen fate perfectly. Sitting 141 million miles from the Sun, about 48 million miles farther than Earth, Mars receives only 43% of the solar energy that Earth does. Surface temperatures average -80 degrees Fahrenheit. The atmosphere became so thin that liquid water can't exist anywhere on the surface. Even the polar ice caps consist mostly of frozen carbon dioxide rather than water ice. This distance sensitivity reveals something profound about planetary habitability. The universe doesn't offer much wiggle room for life-supporting worlds. The margin for error spans less than 2% of orbital distance in either direction. Miss that narrow target by even a small amount, and you get either a boiling hellscape or a frozen wasteland. Computer simulations suggest this extreme sensitivity applies to virtually any star system. Most habitable zones around other stars prove even narrower than our Sun's. Smaller stars emit less energy, while larger stars burn out too quickly for life to evolve. Earth threads the needle in a universe where needles are microscopic and threading them requires absolutely perfect aim. We didn't just get lucky with our orbital distance. We got improbably, almost magically lucky. Stand up and jump. Go ahead, give it a try. When you land back down, you've just experienced one of the universe's most perfectly calibrated forces. Earth's gravity pulls you downward at exactly 9.8 meters per second squared, a rate of acceleration that turns out to be absolutely crucial for making life possible on our planet's surface. This gravitational sweet spot emerges from Earth's diameter of about 8,000 miles. That specific size creates a planet massive enough to generate strong gravity, but not so massive that gravity becomes crushing. Too small, and gravity becomes too weak to hold onto a thick atmosphere. Too large, and gravity becomes so strong that complex life forms can't function properly. Earth's gravity feels perfectly normal to us because we evolved here, but this normal represents an extraordinary cosmic coincidence. If Earth were just 50% larger in diameter while maintaining the same density, surface gravity would increase to about 14.7 meters per second squared. That might not sound dramatically different, but it would fundamentally change how life develops. Larger creatures would become impossible under higher gravity. Birds couldn't achieve flight. Tall trees couldn't pump water to their top branches against increased gravitational pull. Even human-like organisms would develop with shorter, stockier builds and much stronger bones. Their increased effective weight would require this adaptation. The entire trajectory of evolution would shift towards smaller, low-profile life forms. Make Earth 50% smaller instead, and surface gravity drops to roughly 6.5 meters per second squared. This weaker pull would struggle to retain atmospheric gases, especially lighter elements like hydrogen and helium that help regulate atmospheric chemistry. The atmosphere would gradually bleed away into space. This would leave behind a thin, Mars-like environment unsuitable for complex life. But Earth's perfect size creates gravity strong enough to clutch our atmosphere tightly. It remains gentle enough to allow diverse life forms to flourish. This gravitational embrace extends all the way to space. It creates what astronomers call Earth's gravitational sphere of influence, a region extending nearly 600,000 miles from our planet where Earth's gravity dominates over the Sun's gravitational pull. This powerful gravitational field does something remarkable. It captures and holds onto our oversized moon. Without Earth's perfectly calibrated gravity, our planet couldn't maintain the gravitational partnership with the moon. This partnership stabilizes our rotational axis and creates the tidal forces that help drive ocean circulation. Among the thousands of exoplanets we've cataloged, most are either super-Earths with crushing gravity or smaller worlds with gravity too weak to maintain thick atmospheres. Planets with gravity within 20% of Earth's value appear remarkably rare throughout the galaxy. We're standing on a world whose size creates the perfect gravitational environment for complex life. Not too strong, not too weak, but exactly right for creatures like us to evolve, thrive, and occasionally jump just for the fun of it. Every single molecule in Earth's atmosphere is constantly trying to escape to space. Right now, gas molecules are bouncing around at tremendous speeds due to thermal motion. Some move fast enough that they should fly off into the cosmic void, never to return. Yet somehow, Earth manages to hold onto its atmospheric blanket with a grip so perfect that we've maintained breathable air for billions of years. The secret lies in what physicists call escape velocity, the minimum speed an object needs to break free from a planet's gravitational pull. Earth's escape velocity clocks in at exactly 11.2 kilometers per second. That's roughly 25,000 miles per hour. This represents the perfect speed threshold for maintaining a life-supporting atmosphere across geological time. Here's why that specific number proves so crucial. Gas molecules in our atmosphere move at various speeds depending on temperature and molecular weight. Lighter molecules like hydrogen and helium zip around much faster than heavier molecules like nitrogen and oxygen. At Earth's surface temperatures, most atmospheric molecules move far slower than escape velocity, but a small fraction move fast enough to theoretically break free. This is where Earth's perfectly calibrated mass saves the day. Our planet weighs exactly enough to create an escape velocity that's high enough to retain the heavy molecules. These molecules make up our breathable atmosphere, yet low enough that we didn't become a gas giant like Jupiter during our formation. If Earth were just 10% less massive, escape velocity would drop to about 10.5 kilometers per second. This seemingly small change would allow our atmosphere to slowly leak away over hundreds of millions of years. We'd gradually lose our protective atmospheric blanket. We'd end up like Mars, a world that once had a thicker atmosphere but couldn't hold onto it permanently. Make Earth 10% more massive instead, and escape velocity jumps to nearly 12 kilometers per second. This stronger gravitational grip would help our planet capture and retain much more hydrogen and helium during formation. We might have ended up with a thick, crushing atmosphere like Venus, or even developed into a mini gas giant with atmospheric pressures thousands of times greater than what we experience today. But Earth's mass hits the sweet spot that creates what atmospheric scientists call a selective atmosphere. Heavy, life-supporting molecules like nitrogen and oxygen get retained essentially forever. Lighter, potentially problematic molecules like hydrogen and methane can gradually escape over geological time. This natural atmospheric filtering helped Earth develop and maintain the precise gas mixture that makes complex life possible. The proof of this perfect atmospheric retention appears in our planet's geological record. Earth has maintained substantial atmospheric pressure for at least 3.8 billion years. Through ice ages, asteroid impacts, massive volcanic eruptions, and dramatic changes in solar energy output, our atmospheric grip has proved so reliable that it survived conditions that would strip away a less perfectly calibrated atmosphere entirely. Among all the rocky planets in our solar system, only Earth achieved the perfect mass-to-escape velocity ratio. This ratio allows long-term atmospheric stability. We're riding on a planet whose gravitational embrace is calibrated with such precision that it creates exactly the atmospheric conditions complex life requires. Earth spins like a tilted top. Our planet's rotational axis leans 23.5 degrees away from perfectly upright, a seemingly modest angle that creates one of the most important features of our climate: seasons. This gentle planetary tilt delivers the perfect amount of seasonal variation to keep Earth's climate stable and habitable across the entire globe. That 23.5 degree angle might appear arbitrary, like our planet just happened to tip over slightly during formation and stayed that way. But this specific tilt represents another cosmic Goldilocks condition. Too much tilt, and seasonal variations become so extreme that much of Earth becomes uninhabitable during parts of the year. Too little tilt, and we lose the climate regulation that seasons provide. Here's how Earth's tilted dance with the sun creates our seasonal climate regulation. During summer in the northern hemisphere, the northern half of Earth tilts toward the sun. It receives more direct sunlight and longer days. Meanwhile, the southern hemisphere tilts away from the sun. It experiences winter with less direct sunlight and shorter days. 6 months later, the situation reverses as Earth continues its orbital journey. This seasonal seesaw prevents any part of our planet from getting too hot or too cold for too long. Areas that would otherwise become scorching hot deserts get seasonal cooling. Regions that might freeze permanently get regular warming periods. The seasonal variation helps distribute heat more evenly around the globe. It prevents the extreme climate conditions that would make large areas uninhabitable. But what makes Earth's 23.5-degree tilt truly remarkable becomes clear when we examine worlds with different axial tilts. Mars tilts at 25 degrees, very similar to Earth, but experiences much more dramatic seasonal changes. Its thinner atmosphere can't moderate temperature swings effectively. During Martian winter, carbon dioxide actually freezes out of the atmosphere at the poles. This creates seasonal atmospheric pressure changes. Uranus demonstrates the chaos that extreme axial tilt creates. This ice giant tilts 98 degrees, essentially rolling around its orbit on its side. This extreme tilt creates seasons lasting 21 Earth years each. During Uranus's summer, one pole faces the sun continuously for decades. The other pole endures decades of constant darkness. Such extreme seasonal variation would make complex life development impossible. Venus shows us the opposite extreme. With virtually no axial tilt, just 3 degrees, Venus experiences no seasonal variation whatsoever. Combined with its runaway greenhouse atmosphere, this lack of seasonal climate variation helped lock Venus into permanent, hellish conditions with no relief or variation. Earth's 23.5-degree tilt delivers seasonal changes that are dramatic enough to provide climate regulation and weather pattern diversity, yet gentle enough to maintain habitable conditions year-round across most of the planet. This creates the climate stability that allows complex ecosystems to develop and flourish across geological time. Our tilted world performs a cosmic balancing act so precise that it's helped maintain stable, life-friendly conditions for billions of years. Not too tilted, not too upright, but leaning at exactly the right angle to create the seasonal symphony that makes Earth a garden planet in a universe full of climate extremes. Journey with me to the most impossible place in the solar system. We're drilling straight down through 6,400 kilometers of solid rock, through crushing pressures that would flatten a human body instantly, through temperatures hot enough to vaporize any known material. At the very center of this hellish descent lies something that shouldn't exist. A solid metal sphere hotter than the surface of the sun. Earth's inner core measures roughly 1,200 kilometers in diameter. That's about the distance from New York to Miami, but compressed into a perfect sphere of solid iron and nickel. This metallic heart blazes at temperatures around 6,000 degrees Celsius, roughly the same temperature as our sun's visible surface. Any piece of iron exposed to such heat on Earth's surface would vaporize instantly into glowing gas. So why doesn't our planet's iron core melt or boil away? The answer reveals one of physics' most extreme demonstrations: pressure overcoming temperature. The weight of 6,400 kilometers of overlying rock creates pressures at Earth's center reaching 360 gigapascals. That's roughly 3.6 million times greater than atmospheric pressure at sea level. Under these crushing conditions, Iron and nickel atoms get squeezed so tightly together that they form crystalline structures impossible to create anywhere else in the solar system. The pressure literally forces the molten metal to freeze solid despite temperatures that would melt it instantly under normal conditions. It's like nature's ultimate hydraulic press, compressing matter into forms that defy surface world physics. This solid inner core isn't just sitting there passively. As Earth rotates, the inner core spins slightly faster than the rest of the planet. It gains about one extra rotation every 400 years. This differential rotation creates a dynamic interaction with the surrounding liquid metal. It helps power our planet's magnetic field generation. Scientists discovered this solid metal heart only in 1936 by studying how earthquake waves travel through Earth's interior. Seismic waves that should have passed straight through instead got reflected and refracted. This revealed the presence of a solid sphere at our planet's center. We're walking around on top of a world that contains a compressed metal sphere nearly as hot as the sun. It spins at its own rate in the deepest basement of our planetary home. The very existence of this solid inner core helps explain why Earth remained geologically active while Mars and Venus lost their internal energy over billions of years. Our compressed metal heart serves as a reservoir of thermal energy, a crucial component in the geodynamo that protects all surface life from deadly cosmic radiation. 2,000 kilometers above the solid inner core, something extraordinary churns in the darkness. A massive ocean of liquid iron and nickel flows in complex patterns. Heat, rotation, and forces we're only beginning to understand drive these patterns. This isn't just molten metal sloshing around randomly. It's Earth's natural electrical generator, the invisible shield that makes life on our planet possible. This liquid outer core extends from 2,900 kilometers below the surface down to the solid inner core, a spherical shell of molten metal roughly 2,200 kilometers thick. To put that in perspective, this liquid metal ocean could contain all of Earth's surface water thousands of times over. But instead of H2O, it consists of iron and nickel heated to temperatures between 4,000 and 6,000 degrees Celsius, hot enough to melt copper wire instantly. The magic happens when this conducting liquid metal moves through existing magnetic fields. Just like the copper wires spinning inside an electrical generator, the flowing iron creates electrical currents. This process is called electromagnetic induction. These currents, in turn, generate new magnetic fields. When conditions align perfectly, this process becomes self-sustaining. The magnetic field helps drive fluid motion. This strengthens the electrical currents, which amplifies the magnetic field. This natural dynamo has been operating continuously for at least 3.5 billion years, possibly longer. The magnetic field it produces extends tens of thousands of kilometers into space. It creates our magnetosphere, an invisible bubble that deflects the solar wind and cosmic rays. Without this protection, those forces would strip away our atmosphere and sterilize Earth's surface. But here's what makes Earth's geodynamo truly remarkable. It's completely self-regulating. When the magnetic field weakens, changes in fluid flow patterns automatically work to strengthen it. When external conditions change, the system adapts to maintain magnetic protection. This isn't a simple machine with predictable operation. It's a complex adaptive system that responds dynamically to changing conditions. Other planets failed to maintain this crucial magnetic generation. Mars likely had a magnetic field billions of years ago, but its smaller size meant less internal heat to drive fluid motion in its core. The dynamo shut down. The magnetic field disappeared. Solar wind stripped away most of Mars's atmosphere. Venus may still have a partially liquid core, but it rotates so slowly that it can't generate the fluid motions necessary for efficient magnetic field production. Earth alone maintains the perfect combination of size, internal heat, rotation rate, and core composition. This allows it to operate the solar system's most powerful and reliable planetary magnetic generator. This liquid metal ocean churning beneath our feet represents the engine that makes our surface world habitable. Without it, Earth would be just another dead rock orbiting the Sun. Between Earth's metallic core and our familiar rocky surface lies something that challenges our understanding of what solid really means. The mantle, a layer of rock nearly 2,900 kilometers thick. It behaves like an incredibly thick fluid. It flows in massive circulation patterns that reshape our planet's surface across millions of years. This isn't liquid rock like lava. It's solid rock so hot that it creeps and flows like the world's thickest honey. Picture trying to pour cold honey on a winter morning. It flows, but extremely slowly. Now imagine that honey is made of solid rock heated to temperatures between 1,000 and 3,500 degrees Celsius. That's essentially what Earth's mantle does. It flows in super slow motion, driven by heat from the core below and cooled by the surface above. This creates the largest circulation system on our planet. Hot rock rises from the deep mantle. It spreads horizontally when it reaches the cooler upper regions. Then it sinks back down as it cools. These circulation cells, called convection currents, can take hundreds of millions of years to complete one cycle. A piece of rock might rise from near the core mantle boundary, travel horizontally for thousands of kilometers, then sink back to the depths over a timescale longer than complex life has existed on Earth. The mantle contains more than 80% of Earth's total volume. This makes it by far our planet's largest component. If you could somehow remove all the water from Earth's surface and look at our world as a solid sphere, you'd be seeing almost entirely mantle material. The thin crust we live on represents less than 1% of Earth's volume. We're essentially living on the surface skin of a mostly molten rock planet. These slow-motion rock currents drive everything we see happening on Earth's surface. The movement of crustal plates, the formation of mountain ranges, the locations of volcanic activity, the creation and destruction of ocean basins. All of this surface geology gets powered by convection currents flowing through solid rock thousands of kilometers below our feet. What makes Earth's mantle circulation truly extraordinary becomes clear when we compare it to other rocky planets. Venus may still have some mantle convection, but its thick crust prevents the efficient heat transfer that drives active surface geology. Mars cooled so much that its mantle convection largely ceased billions of years ago. This ended most geological activity on its surface. Earth maintains the perfect balance of internal heat and efficient cooling to keep this massive rock ocean in constant, slow motion. The result is a geologically active planet where the surface constantly renews itself. We live on top of a world where the very rocks beneath our feet are flowing like an incredibly thick fluid. They carry heat from Earth's interior to power the geological processes that make our dynamic planet possible. But deep within Earth's interior, something remarkable has been happening every single second for the past 4.6 billion years. Unstable atoms are spontaneously falling apart. They release energy in the process. This isn't a controlled nuclear reaction like in a power plant. It's a natural process of radioactive decay. It transforms Earth's interior into a massive, self-fueled nuclear power source generating roughly 44 trillion watts of continuous energy. The main players in this underground energy production are three radioactive elements scattered throughout Earth's interior: uranium-238, thorium-232, and potassium-40. These unstable isotopes didn't choose to be radioactive. They formed this way during the violent stellar explosions that created the elements heavier than iron. When our solar system condensed from this stellar debris 4.6 billion years ago, Earth inherited a substantial inventory of these natural atomic batteries. Here's how the process works. Uranium-238 has a half-life of 4.5 billion years. This means that half of any sample will decay in that time frame. When a uranium nucleus becomes unstable and splits apart, it releases energy in the form of heat and radiation. It transforms into a series of daughter elements while doing so. Thorium-232 follows a similar process with a half-life of 14 billion years. Potassium-40 decays more quickly, with a half-life of 1.3 billion years. The total energy output from this natural nuclear decay equals about 44,000 nuclear power plants operating simultaneously. That's enough power to supply the entire United States for roughly 4,000 years. And unlike human-built nuclear reactors, Earth's natural reactor comes with no risk of meltdown. It requires no fuel processing. It produces no dangerous waste that needs long-term storage. This radioactive energy serves as the fundamental power source driving almost all of Earth's internal activity. It heats the core enough to keep the outer core liquid and circulating. It drives the convection currents in the mantle that power plate tectonics. It provides the energy that creates volcanic activity and builds mountain ranges. Without radioactive decay, Earth would have cooled and become geologically dead billions of years ago. But here's the truly remarkable part. This natural nuclear power supply is gradually declining in exactly the right way to maintain Earth's habitability. When our planet formed, radioactive decay generated roughly 3 times more heat than it does today. This extra energy helped keep Earth's interior molten during the early bombardment period. Asteroid impacts threatened to freeze our world during this time. As Earth matured and life began to emerge, the declining radioactive heating helped stabilize our planet's temperature. The half-lives of our main radioactive fuel sources are calibrated almost perfectly for planetary evolution. Uranium-238 provides long-term steady heating across billions of years. Potassium-40 provided extra energy during Earth's early development, but is now largely depleted. Thorium-232 will continue supplying energy for many billions of years after the Sun becomes a red giant and destroys Earth's surface. We're living on a world powered by natural nuclear fuel that will keep our planet geologically active for billions of years to come. Earth's radioactive energy depot ensures that our dynamic planet will continue reshaping its surface. It will maintain its magnetic field and support the geological processes that help regulate our climate long into the cosmic future. Take an apple and peel it carefully, trying to remove the thinnest possible layer of skin. That paper-thin peel represents the thickness of Earth's crust compared to our planet's total size. Humanity, along with every living thing we've ever discovered, exists entirely within this impossibly thin rocky shell. It floats on top of an ocean of molten rock thousands of kilometers deep. Earth's crust ranges from just 5 kilometers thick under parts of the ocean floor to about 70 kilometers thick under major mountain ranges like the Himalayas. To put this in perspective, if Earth were the size of a basketball, the crust would be thinner than a piece of paper wrapped around its surface. We're essentially living on the skin of a mostly molten planet. A layer thinner than the distance most people drive to work separates us from temperatures hot enough to vaporize rock. This crustal thinness becomes even more remarkable when you consider what lies beneath. Drill down just a few dozen kilometers, and you'd encounter the mantle. 2,900 kilometers of rock heated to temperatures between 1,000 and 3,500 degrees Celsius. Continue deeper, and you'd reach the outer core. 2,200 kilometers of liquid iron and nickel at temperatures rivaling the surface of the Sun. Finally, at Earth's center, sits the inner core, a solid metal sphere compressed under pressures that would instantly crush any material from the surface world. The deepest humans have ever drilled is about 12 kilometers. That's less than 1/5 of the way through the thinnest parts of the oceanic crust. The Kola Super Deep borehole in Russia, which holds the depth record, reached temperatures of 180 degrees Celsius before drilling equipment became too difficult to operate. That's nowhere near the 1,000-degree boundary where the crust meets the mantle. This thin crust doesn't just sit passively on top of the mantle. It's constantly being created, moved, and recycled by the convection currents flowing in the hot rock below. At mid-ocean ridges, new crust forms as mantle material rises up and solidifies. At subduction zones, old oceanic crust gets pushed back down into the mantle. There it melts and eventually gets recycled into new crustal material. The average age of oceanic crust is only about 60 million years because of this constant recycling process. Continental crust lasts longer. Some areas are over 4 billion years old. But even continents get reshaped and rearranged by the forces operating in the mantle below. Perhaps most remarkably, this paper-thin shell supports not just all known life, but also contains all the fresh water, breathable atmosphere, and moderate temperatures that make Earth habitable. Everything that distinguishes our planet from the hellish interior conditions exists entirely within the outermost 0.4% of Earth's radius. We're living in the cosmic equivalent of a penthouse apartment. Perfect environmental conditions in the thin surface zone of a planet whose interior would instantly vaporize any complex molecule. The fact that this impossibly thin crust remains stable enough to support 4.6 billion years of geological evolution and biological development represents one of the most improbable architectural achievements in the known universe. Our entire existence plays out on the surface skin of a mostly molten world. We're protected from the furnace below by a rocky barrier thinner than an eggshell relative to the size of our planet. Right now, as you read these words, you're under attack. An invisible army of charged particles screams toward Earth at speeds reaching 400 kilometers per second. This solar wind carries enough energy to strip away our atmosphere, sterilize our planet's surface, and turn Earth into a lifeless rock drifting through space. Yet you feel absolutely nothing because Earth deploys the most sophisticated defense system in the known solar system. Our planet's magnetic field extends roughly 60,000 kilometers into space. That's about 5 times Earth's diameter. It creates an invisible fortress that deflects this cosmic bombardment around our world like an umbrella deflecting rain. This magnetosphere operates as Earth's first line of defense. It intercepts solar wind particles traveling at nearly 2 million kilometers per hour. It redirects them safely past our planet. The numbers behind this cosmic protection reveal just how intense the threat really is. During quiet solar conditions, our sun hurls about 1 billion tons of charged particles toward Earth every second. When solar storms erupt, that bombardment can increase by orders of magnitude. It creates particle densities capable of destroying satellite electronics. It threatens astronauts' safety even inside the International Space Station. But Earth's magnetic umbrella doesn't just passively block this assault. It actively channels the incoming particles toward our polar regions. There they interact with atmospheric gases to create the aurora. Those dancing sheets of green, blue, and red light paint the polar skis. What we see as beautiful natural light shows actually represent our planet's defense system at work, safely disposing of deadly cosmic radiation in spectacular displays visible from space. This magnetic protection operates through a process so elegant it seems almost magical. As solar wind particles approach Earth, they encounter our magnetic field lines. They get trapped in spiral paths around those invisible lines of force. Instead of slamming directly into our atmosphere and surface, the particles follow magnetic highways. These highways guide them around Earth and past our planet entirely. The proof of this defense system's importance becomes starkly clear when we examine our planetary neighbors. Mars lost its magnetic field billions of years ago. Solar wind has since stripped away most of its atmosphere. This left behind an environment too thin and cold to support liquid water. Venus never developed a strong planetary magnetic field. Constant solar bombardment helped create its toxic atmospheric pressure cooker. Earth's magnetic umbrella has been operating reliably for at least 3.5 billion years. It protected the gradual development of our atmosphere, oceans, and eventually life itself. Without this invisible shield deflecting cosmic radiation day and night, Earth would have become just another airless rock orbiting the Sun. We live under the protection of the solar system's most effective and long-lasting planetary defense system. A magnetic fortress that never sleeps, never fails, and never asks for recognition. What's in the air around you right now? That mixture of roughly 78% nitrogen and 21% oxygen represents the universe's most carefully calibrated atmospheric cocktail. A recipe so perfectly balanced that changing either ingredient by even a few percentage points would make complex life impossible on Earth's surface. This atmospheric masterpiece didn't happen by accident. It took over 2 billion years of planetary evolution to achieve these precise proportions. Early Earth had virtually no free oxygen in its atmosphere, less than 0.001% compared to today's 21%. The nitrogen was there from the beginning. Volcanic outgassing released it during our planet's formation. But the oxygen that makes energetic life possible had to be manufactured by living organisms themselves. Around 2.5 billion years ago, cyanobacteria figured out how to split water molecules using solar energy. They released oxygen as a waste product. This triggered what scientists call the Great Oxidation Event, an atmospheric revolution that pumped oxygen levels from virtually zero to roughly 21% over hundreds of millions of years. The process could have easily gone wrong in countless ways. Too much oxygen or too little. Here's why the 78-to-21 ratio proves so crucial for life. Pure oxygen would create an atmosphere so reactive that lightning strikes would trigger global fires. Any spark would ignite planetary infernos. Even breathing pure oxygen becomes toxic to most life forms after just hours of exposure. We need oxygen diluted to safe levels. Nitrogen serves as the perfect atmospheric buffer. Chemically stable under normal conditions, it neither helps nor hinders combustion. This creates what atmospheric chemists call a regulated atmosphere. Fire can exist but won't consume everything. Breathing can power complex organisms but won't poison them. But Earth's atmosphere does far more than just provide breathable air. It doubles as the solar system's most effective cosmic debris disposal system. Every day, roughly 100 tons of space dust, micrometeorites, and small rocky fragments rain down on our planet. Most of this cosmic debris comes from asteroid collisions, comet trails, and interplanetary dust. Without our atmosphere, it would accumulate on Earth's surface. Our atmosphere incinerates virtually all of this incoming material before it reaches the ground. Friction with atmospheric gases heats meteoroids to thousands of degrees. It vaporizes them completely in brilliant streaks we call shooting stars. What we see as beautiful meteor showers actually represent our atmosphere working overtime, keeping cosmic debris from cluttering Earth's surface. The thickness and density of our atmosphere creates the perfect balance for this cosmic cleanup service. Too thin, and large meteoroids would reach the surface and crater the landscape like on the moon. Too thick, and our atmosphere would crush surface life under excessive pressure like on Venus. Among the thousands of exoplanet atmospheres we've analyzed, we've found worlds dominated by methane, carbon dioxide, hydrogen, and various toxic combinations. But nowhere have astronomers detected the precise nitrogen-oxygen mixture that makes Earth's atmosphere uniquely suitable for both breathing and cosmic protection. That air you're breathing represents the culmination of a 4.6 billion-year atmospheric engineering project that appears to have succeeded exactly once in the observable universe. About 25 kilometers above your head, something remarkable floats in the thin air of Earth's stratosphere. A gossamer-thin layer of ozone gas so tenuous you could compress it to the thickness of a few sheets of paper. This fragile barrier stands between all surface life and radiation intense enough to sterilize our planet within months. This stratospheric ozone layer contains just 3 oxygen atoms bonded together instead of the usual 2. This creates a molecule with a very special property. It absorbs ultraviolet radiation with deadly efficiency. UVB and UVC radiation from the sun pack enough energy to shred DNA molecules. They destroy cellular proteins. They kill most living organisms through radiation poisoning. Without ozone protection, Earth's surface would receive UV doses lethal to virtually all complex life. The ozone layer performs its protective magic through an elegant chemical dance. When UV radiation strikes an ozone molecule, it gets absorbed and converted to heat. This breaks the ozone temporarily into regular oxygen and a single oxygen atom. But this destruction proves temporary. The separated atoms quickly recombine into new ozone molecules, ready to absorb more UV radiation. The process repeats billions of times per second. It creates a self-regenerating UV shield. This molecular sunscreen blocks roughly 99% of the UVB radiation and virtually all UVC radiation before it can reach Earth's surface. The remaining 1% that gets through provides just enough UV exposure for beneficial processes, like vitamin D synthesis in human skin. It stays below the threshold that would cause widespread radiation damage to living tissues. The remarkable thing about our ozone shield becomes apparent when you consider its incredible thinness. If you could somehow compress all the ozone in Earth's stratosphere down to sea level pressure, it would form a layer just 3 millimeters thick around our entire planet. That's roughly the thickness of 2 pennies stacked together. This impossibly thin chemical barrier stands between surface life and radiation that would otherwise make Earth uninhabitable. But the ozone layer does more than just block radiation. It also helps regulate atmospheric temperature by absorbing UV energy and converting it to heat in the stratosphere. This creates a temperature inversion that helps stabilize our overall atmospheric structure and weather patterns. The ozone heating helps drive stratospheric winds that influence weather systems far below. Other planets lack this crucial UV protection entirely. Mars has virtually no ozone layer. This leaves its surface exposed to sterilizing radiation. Venus has some ozone, but its thick atmosphere absorbs it at lower altitudes where it can't provide surface protection. Among rocky planets in our solar system, only Earth developed and maintains the delicate ozone chemistry necessary to shield surface life from deadly solar UV. The proof of ozone's importance became dramatically clear in the 1980s when scientists discovered that human-made chemicals were depleting the ozone layer over Antarctica. The resulting ozone hole allowed dangerous levels of UV radiation to reach Earth's surface. It threatened everything from phytoplankton in the oceans to human skin cancer rates. We live under the protection of nature's thinnest and most efficient sunscreen, a molecular shield so delicate that it can be disrupted by human activity, yet so crucial that all complex surface life depends on its continued existence. 3 oxygen atoms bonded together in the right place at the right altitude make the difference between a habitable world and a radiation-sterilized wasteland. Press your thumb firmly against a table and notice the sensation. You're experiencing roughly 1 pound of force per square inch, about 1/15 the atmospheric pressure that Earth's entire gaseous envelope exerts on every surface at sea level. This invisible atmospheric weight, measuring exactly 14.7 pounds per square inch, represents one of the universe's most precisely calibrated pressure systems. This atmospheric pressure didn't develop randomly. It emerges from the perfect balance between Earth's gravity, atmospheric mass, and surface area. Our planet holds onto exactly the right amount of gas to create surface pressure that keeps water liquid across the widest possible temperature range. Too little pressure, and water would boil away at normal Earth temperatures. Too much pressure, and our atmosphere would crush surface life under unbearable weight. The 14.7 pounds per square inch standard proves crucial for maintaining liquid water across Earth's surface. Water's boiling point depends directly on atmospheric pressure. Reduce the pressure, and water boils at lower temperatures. On Mars, where atmospheric pressure averages less than 1% of Earth's, water boils immediately upon exposure to the surface environment, even at temperatures well below freezing. But Earth's atmospheric pressure does something even more remarkable. It creates what scientists call the triple-point sweet spot for water. At our surface pressure and temperature range, water can exist simultaneously as solid ice, liquid water, and gaseous vapor. This allows for the complex phase changes that drive our planet's weather systems and water cycle. The weight of our atmosphere also provides essential protection against the vacuum of space. Without atmospheric pressure, human bodies would suffer explosive decompression. Dissolved gases in blood would form bubbles. Bodily fluids would boil. Consciousness would be lost within seconds. Our 14.7 pounds per square inch atmospheric embrace keeps our bodies properly pressurized and functioning. This pressure sweet spot extends to breathing itself. The partial pressure of oxygen at sea level provides exactly the right concentration for efficient gas exchange in human lungs. Climb to high altitude where atmospheric pressure drops significantly and breathing becomes difficult. Reduced pressure means less oxygen available per breath. Descend too deep underwater where pressure increases dramatically, and breathing compressed air becomes dangerous due to nitrogen narcosis. Earth's atmospheric pressure also enables weather systems that distribute heat and moisture around our planet. The pressure differences that drive winds, storms, and ocean currents all depend on our atmosphere having exactly the right weight and density to create these circulation patterns. Too little atmospheric mass, and weather systems become too weak to redistribute energy effectively. Too much mass and crushing pressures would prevent the delicate atmospheric circulation that moderates our climate. Among rocky planets in our solar system, only Earth achieved the perfect atmospheric mass to gravity ratio. This creates surface pressures compatible with liquid water and complex life. Venus developed atmospheric pressures 90 times greater than Earth's, enough to crush human bodies instantly. Mars maintains pressures so low that liquid water cannot exist on its surface. We live at the bottom of an atmospheric ocean whose weight has been calibrated with extraordinary precision. This invisible pressure envelope presses against every surface with exactly the force necessary to maintain the chemical and physical conditions that make Earth's surface habitable. Not too heavy, not too light, but pressing down with exactly the right force to keep our water-based world functioning perfectly. Water behaves unlike any other substance in the universe, and that bizarre behavior saves Earth's life every winter. Most materials become denser as they cool. They contract, get heavier per unit volume, and sink when surrounded by warmer versions of themselves. Water follows this rule down to 4 degrees Celsius, then does something absolutely unprecedented. It reverses course and becomes less dense as it cools further. When it finally freezes at 0 degrees Celsius, ice becomes roughly 9% less dense than liquid water. This means ice floats instead of sinking, a physical property so unusual that it occurs in virtually no other natural substance, so crucial that complex life couldn't exist without it. Here's why this matters for planetary survival. If ice behaved like normal materials and sank when it formed, Earth's oceans would freeze from the bottom up during cold periods. Once ice began accumulating on the seafloor, it would continue building upward until entire ocean basins became solid ice. The resulting snowball Earth conditions would reflect so much solar energy back to space that our planet would remain frozen permanently. Instead, floating ice creates an insulating lid that protects liquid water beneath. When ocean surfaces freeze during winter or ice ages, they form a protective barrier that actually helps maintain liquid water below. Ocean life continues thriving under ice sheets. Thermal circulation continues operating under the frozen surface. The planet maintains unfrozen water reserves that prevent permanent global freezing. Earth's 1.4 billion cubic kilometers of ocean water, enough to cover the entire planet 2.7 kilometers deep if spread evenly, serves as a massive thermal battery. It moderates our planet's temperature. Water has an extraordinarily high specific heat capacity. This means it takes tremendous amounts of energy to change its temperature. This allows our oceans to absorb enormous quantities of heat during summer without warming dramatically, then release that stored heat gradually during winter. This oceanic thermal storage creates climate stability that would be impossible on a dry planet. Continental interiors on Earth experience temperature swings of 40 to 50 degrees Celsius between summer and winter. But areas near large bodies of water experience much gentler temperature variations. Water moderates the extremes in both directions. The global ocean circulation system distributes this thermal energy around our planet through currents that transport warm water toward the poles and cold water toward the equator. The Gulf Stream alone carries roughly 30 times more heat northward than all the world's rivers combined. Without this oceanic heat distribution, polar regions would be far colder and tropical regions would be far hotter. Much of Earth would be uninhabitable. Water's unusual density behavior also drives the deep ocean circulation that helps regulate global climate. Cold. Dense water sinks at the poles and flows along the ocean bottom toward the equator. Warm surface water moves poleward to replace it. This global conveyor belt circulation takes roughly 1,000 years to complete one full cycle. It creates a planetary scale system for mixing heat, nutrients, and dissolved gases. Among known planets and moons, only Earth maintains vast bodies of liquid water with the thermal properties necessary to moderate planetary climate across geological time. Mars had surface water billions of years ago, but lost it when atmospheric pressure dropped too low. Europa and Enceladus have subsurface oceans, but they remain liquid only because of tidal heating, not surface climate regulation. We live on a water world where H2O's bizarre physics creates the thermal stability that complex life requires. Every winter that doesn't freeze our planet solid. Every summer that doesn't boil our oceans away. These represent water's unique properties, maintaining the delicate temperature balance that makes Earth habitable in a universe full of frozen and scorched worlds. Imagine standing on the world's largest moving walkway, one that stretches across entire continents. It operates so slowly you'd never notice it in a human lifetime. Right now, the ground beneath your feet is riding on exactly such a system. Every piece of Earth's surface sits on massive rocky plates. They slide across the planet at roughly the speed your fingernails grow. Forces operating thousands of kilometers below in the churning mantle drive this motion. This planetary conveyor belt system operates through the same physics that drives boiling water in a pot. It is scaled up to work with solid rock across geological time. Deep within Earth's mantle, hot rock rises from the core mantle boundary. This journey takes tens of millions of years to complete. When this superheated material finally reaches the upper mantle, it spreads horizontally beneath Earth's crust, like extremely thick honey oozing across a tabletop. As the hot rock spreads and cools, it eventually becomes dense enough to sink back toward Earth's interior. This completes circulation cells that can span thousands of kilometers. They operate for hundreds of millions of years. These massive convection currents create a slow-motion escalator system. They carry crustal plates along for the ride. They push and pull them across Earth's surface in an endless geological dance. The driving forces behind this crustal motion work through several ingenious mechanisms. At mid-ocean ridges, rising mantle material pushes seafloor plates apart. New oceanic crust forms and spreads outward like a slow-motion zipper opening. At subduction zones, the weight of old, cold oceanic crust helps pull entire plates downward. They sink back into the mantle. They drag the rest of the plate along behind them. But the mantle convection system does more than just move plates around randomly. It operates like a planetary scale recycling center. It constantly creates new crustal material at spreading centers. It destroys old crust at subduction zones. This process ensures Earth's surface never becomes completely covered with ancient, cold crust. It prevents our planet from locking into geological death. The energy driving this massive crustal transportation system comes from the radioactive decay we explored earlier. It also comes from heat left over from Earth's formation. This dual energy source has kept the conveyor belt operating continuously for at least 3 billion years. Earth became the only planet in our solar system with active plate tectonics operating today. Other rocky planets failed to maintain this dynamic crustal motion. Venus developed crust so thick and rigid that it could not form discrete plates. Mars cooled so quickly that mantle convection largely ceased. This ended most geological activity billions of years ago. Only Earth achieved the perfect balance of internal heat, crustal thickness, and surface conditions. It can operate the solar system's only functioning plate tectonic system. We live on a world where the ground beneath our feet participates in the slowest transportation system ever devised, a planetary moving walkway that has been reshaping Earth's surface since complex life first emerged in the oceans. Earth has been undergoing the longest home renovation project in the known universe. For 4.6 billion years, our planet has been continuously remodeling its surface. The processes are so gradual that entire mountain ranges can rise and disappear between major life eras. This is not random geological chaos. It's a sophisticated recycling system that ensures Earth's surface never grows old and stagnant. The renovation operates through two main construction processes working in perfect coordination. At underwater mountain ranges called mid-ocean ridges, Earth literally manufactures new seafloor. It splits apart existing oceanic crust. It fills the gaps with fresh molten rock from below. This seafloor spreading process creates new oceanic crust at rates of 2 to 18 centimeters per year, fast enough to cross a room in a human lifetime, yet slow enough to stay invisible on human timescales. Meanwhile, at opposite edges of ocean basins, the renovation project disposes of old building materials. Subduction zones allow ancient seafloor to slide back into Earth's interior. Oceanic crust that may be 200 million years old, older than the dinosaurs, gets recycled back into the mantle. There it melts and eventually contributes to forming new crust elsewhere. This creates a conveyor belt of crustal renewal. It ensures oceanic crust never grows older than about 200 million years anywhere on Earth. That might sound ancient, but it's young compared to continental crust. Some continental areas date back over 4 billion years. The ocean floors represent Earth's newest surfaces. They are constantly refreshed through this ongoing renovation process. Continental drift adds the final touch to Earth's surface makeover. It moves entire land masses around the planet, like massive puzzle pieces seeking new arrangements. The Atlantic Ocean didn't exist 200 million years ago. North America and Europe were joined together in a supercontinent. As new seafloor formed along the mid-Atlantic ridge, it gradually pushed these continents apart at rates of 2 to 3 centimeters per year. This continental choreography has created and destroyed supercontinents multiple times throughout Earth's history. Pangaea, the most recent supercontinent, began breaking apart around 200 million years ago. Before Pangaea, other supercontinents called Rodinia and Columbia formed and dispersed in earlier chapters of Earth's geological story. Each cycle takes roughly 400 to 600 million years to complete. The surface renovation project does more than rearrange geography. It influences Earth's climate and habitability. When continents cluster together in supercontinents, global climate becomes more extreme. Vast interior deserts and intense monsoon systems develop. When continents disperse around the globe, climate becomes more moderate and stable. No other planet maintains this level of surface renewal activity. Venus shows evidence of massive volcanic resurfacing events. These may have replaced its entire surface within the past billion years. But these appear to be catastrophic events, not continuous renovation. Mars displays ancient surface features billions of years old. This indicates its renovation project shut down early in planetary history. Earth alone operates a surface renewal system sophisticated enough to continuously refresh the planet. It also maintains stable conditions for life. We live on a world that has been renovating itself longer than life has existed in the universe. It creates an ever-changing surface that somehow remains perpetually suitable for habitability. Earth operates the most sophisticated climate control system ever discovered, a planetary thermostat that has maintained habitable temperatures for over 4 billion years. It uses an intricate balance of volcanic emissions and natural carbon dioxide removal. This isn't a simple heating or cooling system. It's a dynamic feedback network. It automatically adjusts atmospheric composition to counteract temperature changes. Without it, our planet would become uninhabitable. The heart of this climate control system lies in Earth's volcanic activity. It serves as a natural CO2 release valve connected to our planet's internal heat engine. When molten rock rises from deep within Earth's mantle, it carries dissolved carbon dioxide. This gets released into the atmosphere during volcanic eruptions. This process pumps roughly 200 to 300 million tons of CO2 into our atmosphere every year, enough to significantly influence global climate if left unchecked. But Earth's climate control system includes an elegant automatic cooling mechanism. As atmospheric CO2 levels rise and global temperatures increase, the enhanced greenhouse effect accelerates chemical weathering of surface rocks. Warmer temperatures and increased rainfall speed up the chemical reactions that break down silicate minerals. These reactions consume CO2 from the atmosphere in the process. The dissolved carbon eventually gets carried to the oceans. There it forms carbonate rocks that lock the carbon away for millions of years. This creates a negative feedback loop that prevents runaway greenhouse heating. More volcanic CO2 leads to warmer temperatures. This accelerates rock weathering, which removes CO2 from the atmosphere, which cools the planet back down. The system automatically adjusts to maintain long-term climate stability. It does this even as volcanic activity varies across geological time. The reverse process works equally elegantly during cooling periods. When global temperatures drop too much, reduced weathering rates mean less CO2 gets removed from the atmosphere. Meanwhile, volcanic activity continues, adding CO2 to the air. The gradual CO2 buildup creates enhanced greenhouse warming. This helps pull Earth out of ice ages and extreme cooling episodes. This planetary thermostat has prevented Earth from experiencing the runaway climate disasters that befell our planetary neighbors. Venus developed a runaway greenhouse effect that boiled away its oceans. It created surface temperatures hot enough to melt lead. Mars lost most of its atmosphere. It became too cold to maintain liquid water on its surface. Earth's volcanic climate control operates on timescales ranging from thousands to millions of years. It provides the long-term climate stability that complex life requires. Short-term climate variations occur within this stable framework. But the underlying volcanic weathering thermostat prevents extreme swings that would sterilize our planet. The system even includes regional climate controls through the strategic placement of volcanic activity. Large volcanic provinces can temporarily cool global climate through sulfur emissions that reflect solar radiation. Ocean ridge volcanism helps drive ocean circulation by heating seawater. Continental volcanism provides the CO2 emissions necessary to prevent permanent global freezing during ice ages. This isn't a perfect climate control system. It operates slowly and allows significant temperature variations over shorter timescales. But it's remarkably effective at maintaining broad climate stability. It has allowed life to evolve and flourish across billions of years. We live on the only known planet with a built-in atmospheric thermostat sophisticated enough to automatically regulate global temperature across geological time. Listen carefully to Earth's pulse, and you'll hear the rhythm of a planet that refuses to grow old. Every earthquake that shakes the ground, every volcanic eruption that lights up the sky, represents our world's internal heart beating with the same strength it possessed billions of years ago. These geological vital signs prove that Earth remains a dynamic, living planet, its rocky neighbors settled into the cosmic equivalent of geological retirement. Roughly 500,000 earthquakes occur on Earth every year, about one earthquake per minute somewhere on our planet's surface. These aren't random acts of geological violence. They're organized expressions of the massive forces operating in Earth's interior. As precise as a doctor's stethoscope detecting a patient's heartbeat, each earthquake represents crustal plates responding to the slow-motion currents flowing thousands of kilometers below in the hot mantle. The global pattern of earthquake activity reveals the anatomy of Earth's plate tectonic system with remarkable clarity. Most earthquakes cluster along plate boundaries where the action happens. Mid-ocean ridges where new seafloor forms, subduction zones where old crust slides back into the interior, transform faults where plates grind past each other horizontally. This seismic network outlines the edges of Earth's crustal plates as clearly as drawing their boundaries on a map. But earthquakes do more than mark plate boundaries. They generate seismic waves that travel through Earth's interior. This allows scientists to map our planet's internal structure with the precision of a medical CT scan. P waves and S waves reveal the location of liquid and solid regions deep within Earth. The way these waves bend and reflect as they travel shows us the boundaries between crust, mantle, outer core, and inner core. Volcanic activity provides equally dramatic evidence of Earth's internal vitality. Roughly 50 to 60 volcanoes erupt somewhere on Earth every year. They bring molten rock from depths of tens to hundreds of kilometers directly to the surface. These aren't random explosions. They're organized expressions of mantle convection, a plate motion, and the chemical cycling that keeps Earth's interior in constant motion. The chemistry of volcanic eruptions tells stories about conditions deep within our planet. Basaltic lavas at mid-ocean ridges reveal the composition of upper mantle rock. More explosive volcanic eruptions at subduction zones show how recycled oceanic crust melts as it sinks back into Earth's interior. Hotspot volcanoes like those in Hawaii provide direct samples of deep mantle material rising from near the core mantle boundary. This geological activity represents something profound. Earth has maintained the internal energy necessary to drive dynamic surface processes for 4.6 billion years. The radioactive decay, thermal convection, and chemical cycling that power our planet's geological vital signs require enormous internal energy across vast timescales. Compare this to our planetary neighbors, and Earth's continued geological vitality becomes remarkable. Mars shows evidence of ancient volcanic activity and earthquakes, but most geological processes shut down billions of years ago. Its interior cooled below critical thresholds. Venus may still have some volcanic activity, but it lacks the organized plate tectonic system that creates Earth's distinctive pattern of controlled geological energy release. The Moon provides a stark example of geological death, a world where internal energy dissipated so completely that the surface became frozen in time billions of years ago. No earthquakes, no volcanic eruptions, no geological processes capable of reshaping the lunar surface. Just ancient impact craters accumulating cosmic dust in eternal stillness. Earth's continuing earthquake and volcanic activity proves our planet's interior remains hot, dynamic, and capable. It can drive the geological processes that make our world habitable. These aren't signs of geological instability. They're vital signs of a planet whose internal engine continues operating at full power. It has done so for nearly 5 billion years of continuous operation. We live on a world whose geological pulse beats strong and steady. It pumps energy from the deep interior to the surface in an endless cycle. It keeps our planet geologically young and dynamically alive. Step outside on a clear night and look up at the moon. What you're seeing shouldn't exist according to everything we know about planetary formation. That bright disk hanging in the sky represents the solar system's most improbable relationship. A satellite so large relative to its parent planet that most astronomers consider it less a moon than the smaller member of a double planet system. Our moon measures roughly 3,474 kilometers in diameter. This makes it about 1/4 the size of Earth. To understand just how bizarre this relationship really is, consider that no other planet in our solar system comes even close to having such an oversized companion. Jupiter's largest moon, Ganymede, spans less than 1/26th of Jupiter's diameter. Saturn's biggest satellite, Titan, measures roughly 1/22nd of Saturn's size. Even the famous Pluto-Charon system, often called a double dwarf planet, features a size ratio of only 1/9. Earth and Moon represent something completely unprecedented in planetary science. If an alien astronomer visited our solar system and examined all the planet-satellite relationships, they would likely reach a startling conclusion. Earth-Moon represents a binary planet system rather than a traditional planet orbiting with a captured asteroid or small moon. This extraordinary size relationship creates gravitational dynamics that simply don't exist elsewhere in our solar system. The Moon exerts tidal forces on Earth roughly 2.2 times stronger than the Sun's tidal influence, despite being 400 times closer than our star. These powerful lunar tides raise and lower our oceans by several meters twice daily. But more importantly, they create stabilizing effects that have shaped Earth's habitability for billions of years. The Moon's large size also means it subtends nearly the same angular size as the Sun when viewed from Earth's surface, a cosmic coincidence so unlikely that it allows for perfect total solar eclipses. During these events, the Moon blocks exactly enough of the Sun's bright disk to reveal the solar corona. This creates one of nature's most spectacular phenomena. This size matching occurs nowhere else in the known universe. But perhaps most remarkably, computer simulations suggest that Earth-sized planets almost never acquire Moon-sized satellites through normal planetary formation processes. The gravitational dynamics that create planetary systems favor small moons, captured asteroids, or no large satellites at all. For Earth to end up with such a massive companion requires extraordinary circumstances that border on the impossible. The Moon's quarter-size relationship with Earth has influenced virtually every aspect of our planet's development, from stabilizing our rotation to driving tidal evolution to influencing the development of life itself. This oversized companion has served as Earth's cosmic partner in creating and maintaining habitability across geological time. We live in a solar system where planetary satellites follow predictable size relationships, except for one glaring exception that breaks every rule and may represent the universe's most unlikely cosmic partnership. Picture the most catastrophic collision imaginable. About 4.5 billion years ago, when Earth was still a molten hellscape barely 100 million years old, a Mars-sized object called Theia slammed into our protoplanet. The impact occurred with such tremendous force that it vaporized both the impactor and a substantial chunk of Earth's outer layers. this cosmic train wreck, happening at speeds of roughly 4 kilometers per second, created the most violent event in our planet's history and gave birth to the Moon. The impact energy from this collision defies comprehension. It released more energy than all the nuclear weapons ever built multiplied by billions. The force was so tremendous that it literally knocked chunks of Earth into orbit. This created a ring of superheated rock vapor and debris circling our battered planet. Temperatures at the impact site reached tens of thousands of degrees, hot enough to vaporize solid rock instantly. Computer simulations of this giant impact reveal the extraordinary physics involved in moon formation. When Theia struck Earth at an oblique angle, the collision didn't just create a crater. It fundamentally restructured both objects. The iron cores of the two bodies merged. The rocky mantles got blasted into space as an expanding cloud of vaporized and molten material. Most of this debris either escaped Earth's gravity entirely or fell back to the surface within hours. But a critical fraction ended up in stable orbit around our planet. It formed a ring of hot rock vapor and molten droplets extending thousands of kilometers into space. This orbital debris cloud looked nothing like the solid moon we see today. It resembled a glowing ring system made of liquid rock rather than ice particles. Over the following thousands of years, this debris ring underwent a remarkable transformation. The vaporized rock gradually condensed into solid particles. These particles then began clumping together through gravitational attraction. Larger chunks grew by sweeping up smaller debris in their orbital paths. Within roughly 100,000 years, incredibly fast by geological standards, most of the ring material had accreted into a single large satellite. It orbited about 15,000 kilometers from Earth's surface. This formation process explains several puzzling features of the Earth-Moon system. The Moon's composition closely matches Earth's mantle rocks. This supports the idea that lunar material originally came from our planet. The Moon has a much smaller iron core relative to its size compared to other rocky bodies. This is consistent with most of the iron from the collision remaining with Earth during the core merger. The giant impact theory also explains why the Earth-Moon system has such unusual angular momentum, why our planet spins relatively quickly, and why the Moon orbits relatively far from Earth. The collision imparted tremendous rotational energy to the system. It sped up Earth's rotation and flung the newly formed Moon into a distant orbit. No other satellite in our solar system shows evidence of such a violent formation process. Most moons appear to be either captured asteroids or objects that formed alongside their parent planets through gentler accretion processes. The Moon represents the only known satellite that literally emerged from the cosmic equivalent of a planetary car crash. Earth wobbles as it spins through space, but that wobble remains remarkably gentle and predictable. This stability exists thanks to our oversized lunar companion acting as a cosmic stabilizer. Without the Moon's gravitational influence, our planet would tumble chaotically through space like a top running out of energy. This would create climate swings so extreme that complex life could never gain a foothold on our world's surface. The Moon's stabilizing influence operates through a process called tidal locking that extends far beyond the familiar ocean tides. Our large satellite exerts gravitational forces strong enough to create a slight bulge in Earth's shape. Not just in the oceans, but in the solid rock of our planet itself. This tidal bulge acts like a gyroscopic stabilizer. It resists changes to Earth's rotational axis through the same physics that keeps a spinning bicycle wheel upright. Earth's rotational axis currently tilts 23.5 degrees from perfectly upright, an inclination that creates our moderate seasonal variations. Without lunar stabilization, this axial tilt would vary chaotically between 0 and 85 degrees, over periods of tens of thousands to millions of years. During high tilt periods, polar regions would experience months of continuous daylight followed by months of total darkness. Equatorial regions would endure temperature swings of hundreds of degrees between summer and winter. The dramatic effects of unstable axial tilt become apparent when we examine Mars. Mars lacks a large stabilizing moon. Its rotational axis varies between 15 and 35 degrees over periods of roughly 100,000 years. This contributes to extreme climate variations that help explain why the red planet lost most of its atmosphere and surface water. During high tilt periods, Martian polar ice caps can completely sublimate. This dramatically changes atmospheric pressure and weather patterns. But lunar stabilization provides Earth with more than just steady seasons. The Moon's gravitational influence has been gradually slowing Earth's rotation over geological time. It extended our day length from the original 5 to 6 hours after the Moon's formation to the current 24 hours. This rotational slowing helped create more moderate temperature differences between day and night. It made Earth's surface more hospitable for life. The lunar tidal forces also dissipate rotational energy through friction. This prevents Earth from spinning so rapidly that centrifugal forces would flatten our planet into a plate spheroid. Without this gradual energy dissipation, Earth might rotate so quickly that equatorial regions would experience significantly reduced gravity. This would fundamentally alter atmospheric circulation and ocean currents. Computer models of Earth's climate without lunar stabilization reveal a world of extremes. Ice ages and greenhouse periods would alternate unpredictably. During low tilt periods, permanent ice caps would extend nearly to the equator. During high tilt periods, polar regions would become scorching hot, while equatorial zones might paradoxically become cooler due to altered atmospheric circulation patterns. The Moon's stabilizing influence extends to Earth's magnetic field as well. The steady rotational dynamics maintained by lunar tidal forces help ensure consistent convection patterns in Earth's liquid outer core. This supports the reliable magnetic field generation that protects our atmosphere from solar wind erosion. Among rocky planets in our solar system, only Earth enjoys the rotational stability provided by a large satellite. Venus rotates so slowly that it lacks meaningful seasons entirely. Its rotation direction is actually reversed compared to its orbital motion. Mars experiences chaotic climate variations, partly due to its unstable axial tilt. We live on a planet whose cosmic gyroscope has been operating reliably for over 4 billion years, maintaining the rotational stability that creates predictable seasons, moderate day-night temperature variations, and the long-term climate consistency that complex life requires to evolve and flourish. Twice each day, the Moon performs an extraordinary magic trick. Lunar gravity raises and lowers sea levels by several meters along coastlines worldwide. This exposes and submerges vast intertidal zones that serve as natural laboratories for evolutionary innovation. These tidal environments created the perfect stepping stones that allowed life to make its greatest leap. The transition from sea to land. The intertidal zone represents one of Earth's most challenging and rewarding habitats. Organisms living here must survive being alternately submerged in seawater and exposed to air. They experience dramatic changes in temperature, salinity, moisture, and oxygen availability twice daily. These harsh conditions create evolutionary pressure that drives rapid adaptation and innovation among intertidal species. Tidal pools scattered across rocky shores serve as miniature worlds where marine life learns to cope with terrestrial conditions. Sea anemones close their bodies during low tide to retain water. Crabs scurry between pools seeking refuge from desiccation. Marine algae develop waxy coatings to prevent water loss during aerial exposure. These adaptations represent evolutionary stepping stones toward full terrestrial life. The Moon's tidal forces create a gradient of habitats ranging from permanently submerged subtidal zones to rarely flooded supratidal areas. This environmental gradient provides a natural escalator that allows marine organisms to gradually adapt to increasingly terrestrial conditions. Species can evolve in the relatively easy lower intertidal zone, then progressively colonize higher zones as they develop better terrestrial adaptations. Ancient tidal environments likely played a crucial role in some of evolution's most important transitions. The first plants to colonize land probably evolved from green algae that originally inhabited tidal pools and splash zones. Early arthropods may have used tidal environments as stepping stones during their transition from marine to terrestrial lifestyles. Even vertebrates might have first ventured onto land by following tidal zones during seasonal migrations. But tidal environments do more than just facilitate evolutionary transitions. They maintain some of Earth's most productive ecosystems. Intertidal zones support extraordinary biodiversity despite their harsh conditions. The twice-daily mixing of nutrients. The constant physical disturbance that prevents any single species from dominating. The steep environmental gradients. All contribute to creating biological hotspots along coastlines worldwide. The Moon's tidal influence also drives crucial ecological processes that extend far beyond intertidal zones. Tidal currents help circulate nutrients and oxygen through coastal waters. Tidal mixing brings deep, nutrient-rich waters to the surface, where they support marine food webs. The predictable rhythm of tides helps synchronize reproductive cycles in many marine species. Other planets and moons lack the strong, regular tidal forces that create these dynamic transitional environments. Mars has negligible tides due to its tiny moons. Venus lacks any moons entirely. Even Earth's ocean world analogs like Europa experience tidal forces from Jupiter. But these operate on longer timescales and lack the regular day-night cycle that makes Earth's tides so effective at creating evolutionary opportunity. The twice-daily tidal cycle also provided early life with a natural timekeeping system. This may help drive the evolution of biological clocks. Many intertidal organisms still follow tidal rhythms in their behavior and physiology. This suggests these cycles became deeply embedded in terrestrial life during the evolutionary transition from sea to land. We live on a world where the Moon creates twice-daily opportunities for evolutionary innovation. It maintains dynamic transition zones that continue serving as Earth's natural laboratories for adaptation and diversification. Close your eyes and imagine Earth without its lunar companion. No gentle moonlight illuminating nighttime landscapes. No reliable tides marking the rhythm of coastal life. But the absence of romantic moonlit evenings would be the least of our problems. A moonless Earth would be a world of such extreme climate chaos that complex life might never have evolved at all. Without lunar stabilization, Earth's rotational axis would wander chaotically across the sky like a spinning top running down. Our planet's tilt could vary anywhere from 0 to 85 degrees over periods ranging from thousands to millions of years. During minimum tilt periods, Earth would have virtually no seasons. Equatorial regions would remain hot year-round, while polar areas stayed frozen in permanent winter. But the maximum tilt scenarios create truly horrifying climate conditions. When Earth's axis tilted to 60 degrees or more, polar regions would point directly toward the sun during summer. They would experience months of continuous daylight with temperatures hot enough to melt polar ice caps completely. Meanwhile, the same polar regions would endure months of total darkness during winter. Temperatures cold enough to freeze carbon dioxide from the atmosphere. The equatorial regions wouldn't escape this climate chaos. During high tilt periods, Earth's equator would experience temperatures swings of hundreds of degrees between summer and winter. Tropical rainforests would alternate between scorching deserts and frozen wastelands depending on Earth's position in its orbit around the sun. No ecosystem could adapt to such extreme and unpredictable climate variations. A moonless Earth would also spin much faster than our current 24-hour day. Without lunar tidal forces gradually slowing our planet's rotation, Earth might still rotate every 5 to 8 hours like it did shortly after formation. These rapid rotations would create ferocious weather systems with wind speeds potentially exceeding 500 kilometers per hour. The centrifugal force from such rapid spinning would bulge Earth's equator outward and flatten the polar regions. This would fundamentally alter our planet's shape. The absence of tides would eliminate one of Earth's most important evolutionary laboratories. Without intertidal zones, life might never have developed the adaptations necessary to transition from sea to land. Marine organisms would lack the twice-daily environmental challenges that drive rapid evolutionary innovation. Coastal ecosystems would lose the nutrient mixing and habitat diversity that tides provide. Ocean circulation patterns would be completely different without tidal mixing. Many coastal areas would become stagnant. They would lack the tidal currents that bring fresh nutrients and oxygen to marine ecosystems. Deep ocean circulation might be significantly weaker without tidal pumping to help drive the global conveyor belt circulation that distributes heat around our planet. Even Earth's magnetic field might be less stable without lunar influence. The steady rotational dynamics that the Moon helps maintain could be important for consistent convection patterns in Earth's liquid outer core. A chaotically tumbling planet might experience more frequent magnetic field reversals or even complete magnetic field collapse. The geological consequences of a moonless Earth would extend to crustal dynamics as well. Without tidal flexing, Earth's crust would experience less stress cycling. This might reduce earthquake activity and volcanic outgassing. This might sound beneficial, but reduced volcanism could mean less CO2 cycling and weaker long-term climate regulation. Perhaps most disturbing of all, a moonless Earth would lack the gravitational anchor that prevents our planet from wandering into different orbital configurations. Computer simulations suggest that without the Moon's stabilizing influence, Earth's orbit around the Sun could become more elliptical over long timescales. This would create additional climate instability. We live in a universe where Earth randomly acquired the exact companion necessary to maintain rotational stability. Moderate climate variations and evolutionary opportunity zones remove that cosmic partner, and Earth becomes a world of such extreme climate chaos that the stable conditions necessary for complex life might never develop. The Moon represents more than just Earth's satellite. It's our planet's cosmic insurance policy against the type of chaotic climate variations that would make complex life impossible. We orbit the Sun as part of a stable double-planet system that created and maintains the predictable environmental conditions that made our existence possible. 4 billion years ago, Earth resembled nothing like the blue marble we see in space photos today. Our planet was a molten nightmare, a hellscape of lava oceans, asteroid bombardments, and toxic atmospheric chemistry that would instantly kill any life form we know today. Yet somewhere in this cosmic inferno, something miraculous happened, something that has never been replicated in any laboratory or observed on any other world. Life began. The early Earth that witnessed life's first spark would have been utterly alien to modern eyes. Surface temperatures reached 1,200 degrees Celsius, hot enough to melt copper. The atmosphere consisted of methane, ammonia, hydrogen sulfide, and virtually no free oxygen. Asteroids the size of mountains slammed into Earth's surface regularly. They vaporized anything unlucky enough to be in their path. The entire planet resembled a volcanic forge operating at maximum intensity. But hidden within this chaos lay the perfect chemistry lab for creating life's building blocks. Lightning strikes, far more frequent and powerful than today, provided energy to spark chemical reactions in the toxic atmosphere. Volcanic vents pumped sulfur compounds and minerals into primitive oceans. Underwater hot springs created temperature gradients that could drive complex chemical processes. All the ingredients for organic chemistry were present, just waiting for the right combination to spark self-replicating chemistry. The transition from complex chemistry to actual life remains one of science's greatest mysteries. Somehow, simple organic molecules learn to make copies of themselves. This self-replication represents the defining moment when chemistry became biology. When collections of molecules became primitive organisms capable of reproduction, mutation, and evolution. Scientists have proposed numerous theories for how this chemical magic trick occurred. Deep-sea hydrothermal vents might have provided the energy and mineral catalysts necessary to build the first self-replicating molecules. Clay surfaces could have served as templates that helped organize simple chemicals into more complex structures. Cycles of wetting and drying in tidal pools might have concentrated organic molecules until they reached critical thresholds for self-organization. But regardless of exactly how it happened, the result was unprecedented in the known universe. Earth became home to the first chemical systems capable of reproduction, evolution, and increasing complexity. These weren't recognizable life forms by modern standards. No cells with membranes, no DNA, no photosynthesis. Just simple molecular machines that could make copies of themselves with occasional errors that allowed for evolutionary change. What makes this achievement truly extraordinary becomes clear when we consider how many things had to go right simultaneously. The chemistry had to be complex enough to support self-replication, but stable enough that the first reproducing molecules didn't immediately destroy themselves. The environment had to provide energy sources without being so violent that it constantly disrupted delicate chemical processes. The first life forms had to solve fundamental problems that continue challenging scientists today. How do you store information chemically? How do you replicate that information accurately? How do you obtain energy from the environment to power these processes? How do you maintain organization in a universe that tends toward chaos? Somehow, in the cosmic equivalent of a blast furnace, Earth's first organisms figured out solutions to these problems. Solutions so effective they've persisted for nearly 4 billion years. Every living thing on Earth today, from bacteria to blue whales, traces its ancestry back to those first self-replicating molecular systems. They emerged from primordial chaos and began the longest-running evolutionary experiment in the observable universe. For nearly a billion years after life began, Earth remained a world that would suffocate any complex organism instantly. The atmosphere contained virtually no free oxygen, less than 0.001% compared to today's 21%. Most early life forms were anaerobic bacteria that thrived in the oxygen-free environment. They extracted energy from sulfur compounds, methane, and other chemicals abundant in the early oceans. Then, around 3.5 billion years ago, a group of microorganisms called cyanobacteria invented a process that would fundamentally transform our entire planet. These microscopic blue-green bacteria figured out how to capture energy directly from sunlight. They used a process we now call photosynthesis. But this wasn't just another way to make a living. It was a revolutionary technology that split water molecules to extract electrons. It released oxygen as a waste product. For the first time in Earth's history, living organisms began pumping free oxygen into the atmosphere at unprecedented rates. The cyanobacteria had no idea they were about to trigger the most dramatic environmental catastrophe in Earth's history. To the anaerobic life forms that dominated early Earth, oxygen was a highly toxic poison. Free oxygen reacts aggressively with organic molecules. It destroys cellular structures and kills organisms that lack protective mechanisms against oxidative damage. The cyanobacteria were essentially conducting chemical warfare against most other life on the planet. This oxygen poisoning event, known as the Great Oxidation Event, began around 2.4 billion years ago. It lasted for nearly a billion years. Atmospheric oxygen levels rose from essentially zero to roughly 10% of current levels. Enough to kill most of the anaerobic organisms that had previously dominated Earth's biosphere. Entire ecosystems collapsed as oxygen-producing bacteria outcompeted oxygen-sensitive life forms for resources and habitat. But the Great Oxidation Event did more than just reorganize the biosphere. It fundamentally changed Earth's atmospheric and surface chemistry. Free oxygen began reacting with iron dissolved in the oceans. This created vast deposits of rust that settled to the seafloor. These banded iron formations represent some of the largest mineral deposits on Earth. They serve as geological monuments to the moment when biology began influencing planetary chemistry on a global scale. The rising oxygen levels also triggered Earth's first global ice age. Oxygen reacted with methane in the atmosphere. This destroyed the powerful greenhouse gas and caused global temperatures to plummet. Ice sheets extended nearly to the equator during this snowball Earth period. Conditions became so harsh that complex life nearly went extinct entirely. Yet somehow life survived this atmospheric revolution. Eventually it learned to thrive in the oxygen-rich environment that cyanobacteria created. Organisms evolved protective mechanisms against oxygen damage. They eventually figured out how to use oxygen's reactive properties to extract far more energy from food molecules. Aerobic respiration, the process that powers complex life today, became possible only after cyanobacteria filled the atmosphere with their toxic waste product. The oxygen revolution also created the ozone layer that protects Earth's surface from deadly ultraviolet radiation. High-energy UV light splits oxygen molecules in the upper atmosphere. This creates ozone that absorbs future UV radiation before it can reach the surface. This UV shield made it possible for life to eventually colonize land without being sterilized by solar radiation. No other planet shows evidence of biological oxygen production at this scale. Mars may have had some oxygen in its early atmosphere, but nothing approaching Earth's current levels. Venus never developed oxygen-producing life. It remained locked in a carbon dioxide greenhouse. Among thousands of exoplanets we've discovered, Atmospheric oxygen remains the most reliable signature of active photosynthetic life. We breathe the waste product of ancient bacteria that accidentally created the atmospheric conditions necessary for complex life. Earth has tried to kill all complex life at least 6 times in the past 500 million years. Massive volcanic eruptions that darkened skies for decades, asteroid impacts that vaporize continents, ice ages that locked the planet in near-permanent freeze, ocean chemistry changes that turned seas into toxic death zones. Each of these mass extinction events eliminated 70 to 95% of all species on Earth. They created biological bottlenecks so severe that complex life survival seems almost miraculous. The most famous extinction event occurred 66 million years ago when a 10-kilometer asteroid slammed into the Yucatan Peninsula. The impact carried the force of billions of nuclear weapons. It vaporized thousands of cubic kilometers of rock. It launched debris into space and triggered global wildfires. A nuclear winter followed as particulates blocked sunlight for months. Photosynthesis collapsed and food webs disintegrated. This cosmic catastrophe ended the age of dinosaurs and eliminated roughly 75% of all species on Earth. But the asteroid impact that killed the dinosaurs wasn't even the worst extinction event in Earth's history. The Permian extinction 252 million years ago eliminated over 95% of marine species and 70% of terrestrial species. Scientists call it the Great Dying because it was so thorough. Massive volcanic eruptions in Siberia pumped toxic gases and greenhouse compounds into the atmosphere for nearly 1 million years. Ocean temperatures rose by 8 degrees Celsius. Ocean chemistry became so acidic that most marine organisms simply dissolved. Each mass extinction created biological bottlenecks that should have ended complex life permanently. When 90% or more of species disappear, the remaining survivors face inbreeding depression, loss of genetic diversity, ecosystem collapse, competition for drastically reduced resources. Mathematical models suggest that complex ecosystems experiencing such severe population crashes should spiral in complete collapse rather than recovering. Yet somehow, life not only survived these repeated near-death experiences, but used them as opportunities for evolutionary innovation. The extinction that ended the Permian period cleared ecological niches. This allowed archosaurs, the group that would eventually produce dinosaurs, to diversify and dominate terrestrial ecosystems. The asteroid impact that killed non-bird dinosaurs created opportunities for mammals to radiate into larger body sizes and new ecological roles. This pattern of extinction and recovery reveals one of life's most remarkable properties: evolutionary resilience. Even when environmental catastrophes eliminate most existing species, the survivors often possess genetic and physiological diversity that allows rapid adaptation to post-extinction conditions. Small, generalist species with broad environmental tolerances and high reproductive rates typically survive mass extinctions better than large, specialized organisms. The recovery periods following mass extinctions also demonstrate life's capacity for evolutionary experimentation. When ecological niches become empty due to species loss, natural selection favors organisms that can exploit these vacant opportunities. This often leads to rapid evolutionary radiation as surviving lineages diversify to fill available ecological roles. Perhaps most remarkably, each extinction recovery cycle has generally resulted in greater biological complexity and diversity than existed before the extinction event. The Cambrian explosion that produced most modern animal body plans occurred after a series of severe extinction events in the late Precambrian. The diversification of mammals following the dinosaur extinction created the complex terrestrial ecosystems that exist today. Life's survival through multiple near-extinction events required not just biological resilience, but also planetary-scale environmental recovery. Earth's climate system, ocean chemistry, and atmospheric composition had to return to ranges compatible with complex life after each catastrophic disruption. The fact that our planet's environmental systems proved capable of recovering from such extreme perturbations suggests remarkable stability in Earth's fundamental habitability mechanisms. We live on a world where life has proven tougher than cosmic impacts, more resilient than volcanic apocalypses, more adaptable than climate catastrophes. The complex organisms surrounding us today represent the descendants of ultimate survivors. Species that endured the worst environmental disasters our planet could produce and emerged stronger, more diverse, and more sophisticated than ever before. For over 3 billion years, Earth's oceans teemed with nothing more exciting than bacteria, algae, and simple multicellular blobs. Life existed, but it was microscopic, soft-bodied, and utterly unrecognizable by modern standards. Then, beginning around 540 million years ago, something extraordinary happened in Earth's seas. In a geological instant, a mere 20 million years, virtually every major animal group we recognize today burst onto the scene, the most spectacular biological debut in our planet's history. This evolutionary explosion, known as the Cambrian period, represents one of the most dramatic transitions in life's history. Before the Cambrian, the fossil record shows mostly bacterial mats and enigmatic soft-bodied organisms that left few traces. After the Cambrian, the fossil record explodes with shells, spines, eyes, claws, jointed legs, and sophisticated predator-prey relationships. It's as if evolution suddenly discovered how to build complex animals and went on the ultimate creative binge. The Cambrian seas became Earth's first biological arms race. Predators evolved sophisticated sensory systems. The first complex eyes capable of forming images appeared during this period. A pre-species responded by developing protective shells, spines, and armor plating. The trilobites, arthropods with compound eyes and jointed legs, became the dominant predators. Anomalocaris, a meter-long swimming predator with grasping arms and circular jaws, terrorized Cambrian seafloors like a prehistoric kraken. But the Cambrian explosion wasn't just about bigger or more fearsome animals. It was fundamentally about biological innovation on an unprecedented scale. Almost every major animal body plan that exists today, from the basic vertebrate design to arthropod jointed appendages to mollusk shells, originated during this brief period. The genetic and developmental toolkits that still govern animal construction today were largely assembled during the Cambrian radiation. What triggered this biological Big Bang remains one of evolution's great mysteries. Rising oxygen levels may have finally reached thresholds necessary to support larger, more active organisms. The evolution of predation itself might have driven an ecological arms race that favored increasingly sophisticated attack and defense strategies. Changes in ocean chemistry could have made it easier for organisms to build shells and hard parts that preserve well in the fossil record. The Cambrian explosion also marks the first time that vision became a major evolutionary force. Simple light-detecting eye spots had existed before, but the Cambrian saw the evolution of image, forming eyes capable of detecting prey, predators, and mates with remarkable precision. This visual revolution transformed how animals interacted with their environment and each other. It drove rapid evolution in behavior, body patterns, and ecological strategies. Perhaps most remarkably, Many Cambrian animals experimented with body plans that have no modern equivalents. Opabinia had 5 eyes and a vacuum cleaner like proboscis ending in a grasping claw. Waywaxia looked like a medieval knight's helmet covered in spines and scales. Hallucigenia walked on 7 pairs of spiny stilts while defensive spikes protected its back. These experimental designs suggest that early animal evolution explored biological possibilities that were later abandoned as more efficient body plans emerged. The Cambrian fossil deposits, particularly the famous Burgess Shale in Canada, preserve soft tissues with exquisite detail. They provide unprecedented windows into ancient ecosystems. These fossil sites reveal complex marine communities with sophisticated predator-prey relationships, behavioral adaptations, and ecological interactions that rival modern ecosystems in their complexity. By the end of the Cambrian period, Earth's oceans had been transformed from bacterial gardens into complex ecosystems dominated by animals that would be recognizable to modern eyes. Arthropods scuttled across seafloors. Mollusks filtered food from the water column. Early vertebrates swam through open waters. The basic ecological structures that still govern marine ecosystems today had been established. The Cambrian explosion demonstrates evolution's capacity for rapid innovation when environmental conditions align with biological potential. In just 20 million years, a brief moment in Earth's 4.6 billion-year history, life progressed from simple multicellular organisms to complex animals. Animals with sophisticated sensory systems, protective armor, and intricate ecological relationships. We live in a world where virtually every animal we see, from insects to elephants, traces its basic body plan back to evolutionary innovations that occurred during the Cambrian explosion. The greatest biological show on Earth happened 540 million years ago. We're still watching the encore performances of that ancient creative burst. When astronomers first started discovering planets beyond our solar system, they expected to find lots of worlds like Earth. Rocky planets with moderate climates and breathable atmospheres. Instead, they discovered something far more common and far more hostile. Super-Earths. These planets, typically 1.5 to 4 times Earth's diameter, seemed like they should be even better for life than our home world. More gravity to hold onto atmospheres, more internal heat to drive geological activity, more surface area for potential habitability. But super-Earths turned into cosmic ovens that would instantly vaporize any Earth-based life form. The problem isn't their size. It's what their size allows them to do during planetary formation. Larger planets have stronger gravity. This means they can capture and retain much more hydrogen and helium from the protoplanetary disk, where they form. While Earth was too small to hold onto these light gases permanently, super-Earths grabbed them and never let go. This creates atmospheric nightmares that make Venus look like a tropical paradise. Super-Earths typically develop hydrogen atmospheres hundreds of times thicker than Earth's entire atmosphere. All that hydrogen acts like a blanket wrapped around a blast furnace. It traps heat so effectively that surface temperatures soar to 1,000 degrees Celsius or higher. That's hot enough to melt copper, zinc, and most common metals. The hydrogen greenhouse effect operates far more efficiently than the carbon dioxide greenhouse that turned Venus into a hellscape. Hydrogen molecules are excellent at absorbing infrared radiation in wavelength ranges where Earth's atmosphere is relatively transparent. This means super-Earth atmospheres trap heat that would otherwise escape to space. They create runaway greenhouse conditions that persist for billions of years. But the atmospheric problems get even worse. These thick hydrogen atmospheres create crushing surface pressures that can exceed 100 times Earth's atmospheric pressure. Any liquid water would be compressed into exotic high-pressure phases that bear no resemblance to the liquid water that makes Earth's oceans. The combination of extreme temperature and pressure creates surface conditions more like the interior of a gas giant than anything resembling a habitable world. The super-Earth atmospheric death trap persists because these planets can't lose their hydrogen envelopes once they acquire them. Earth-sized planets can gradually lose light atmospheric gases to space through various escape processes. But super-Earths have such strong gravity that they lock their hydrogen atmospheres in place permanently. Even intense stellar radiation that would strip atmosphere from smaller planets can't overcome the gravitational grip that super-Earths maintain on their gaseous envelopes. Recent observations of super-Earth atmospheres using advanced telescopes confirm these theoretical predictions. Planets like 55 Cancri e and GJ1214b show spectroscopic evidence of thick hydrogen-dominated atmospheres, surface temperatures exceeding 1,000 degrees Celsius. These worlds represent cosmic furnaces, where any complex molecules would decompose instantly into simple atoms. The prevalence of super-Earths throughout the galaxy suggests that Earth-sized planets may be cosmically rare. Most planetary formation processes seem to favor creating planets larger than Earth. This means most rocky worlds end up trapped in the super-Earth hydrogen greenhouse hell. They do not develop the moderate conditions necessary for life. We live on a planet that's apparently too small to be typical, but exactly the right size to avoid the atmospheric death trap that destroys habitability on most rocky worlds throughout the galaxy. Red dwarf stars seemed like perfect candidates for hosting habitable worlds. They burn fuel so efficiently that they'll shine for trillions of years, giving any potential life forms plenty of time to evolve and flourish. They're also the most common type of star in our galaxy, comprising roughly 75% of all stellar objects. With such abundance and longevity, red dwarf systems should be cosmic suburbs teeming with life. Instead, they've become gravitational prisons that trap planets in temperature extremes that make habitability virtually impossible. The problem emerges from red dwarf stars being much smaller and dimmer than our Sun. For a planet to receive enough energy to maintain liquid water, it must orbit extremely close to its red dwarf host, typically within a few million kilometers. Compare this to Earth's 150 million kilometers distance from the Sun. But orbiting so close to any star creates a gravitational death sentence. Tidal locking. Tidal forces from the nearby star gradually slow the planet's rotation until one side permanently faces the star, while the other side remains in eternal darkness. This process is similar to how the Moon became tidally locked to Earth. It transforms red dwarf planets into worlds of impossible extremes. The star-facing hemisphere becomes a furnace with temperatures exceeding 1,000 degrees Celsius. The dark side freezes to temperatures approaching absolute zero. These tidally locked worlds develop atmospheric dynamics unlike anything in our solar system. On the day side, any remaining atmosphere gets superheated and rises to extreme altitudes. Powerful winds, potentially exceeding hurricane force velocities, carry this heated gas toward the night side where it cools and condenses. But the temperature differential is so extreme that most atmospheric components freeze solid on the night side. This gradually removes gas from the atmosphere entirely. The day-night terminator line, the boundary between the scorched day side and frozen night side, becomes the only zone where temperatures might theoretically allow liquid water. But this twilight zone experiences constant hurricane-force winds as heated day-side atmosphere rushes toward the frozen night side. Any surface water would be blown away by winds that could exceed 500 kilometers per hour. Even if liquid water somehow persisted in the terminator zone, the extreme stellar radiation from being so close to the star would create additional habitability challenges. Red dwarf stars, though cooler than the Sun, often produce powerful stellar flares. These flares unleash intense X-ray and ultraviolet radiation. Planets orbiting close enough to receive adequate heat also orbit close enough to receive sterilizing doses of high-energy radiation during flare events. The atmospheric stripping caused by stellar radiation becomes particularly devastating for tidally locked planets. The permanently star-facing hemisphere receives continuous bombardment of stellar wind particles and radiation. Without the protection of a strong magnetic field, which many small planets lack, this constant assault gradually strips away any atmosphere the planet might have retained. Computer climate models of tidally locked planets reveal atmospheric collapse scenarios. In these, virtually all gases eventually freeze out on the night side or get stripped away by stellar radiation. Even thick atmospheres that might initially survive tidal locking tend to destabilize over millions of years. This leaves behind airless worlds with extreme day-night temperature contrasts. Recent observations of red dwarf planets using infrared telescopes have detected exactly these predicted conditions. Planets like TRAPPISS 1b show evidence of minimal atmospheres and extreme temperature differences between day and night sides. The few red dwarf planets that do retain atmospheres often show signs of atmospheric circulations so violent that surface conditions remain hostile to any conceivable form of life. Among the thousands of red dwarf planets discovered so far, none show convincing evidence of the atmospheric stability necessary to maintain liquid water across geological time. We orbit a star large and bright enough that Earth can maintain liquid water while remaining far enough away to avoid tidal locking, a distance relationship that appears to be cosmically rare among the galaxy's most common stellar systems. When planet hunters discovered the first worlds orbiting other stars in the 1990s, they expected to find solar systems that looked roughly like ours. Small rocky planets close to the star, gas giants farther out, stable circular orbits that remained unchanged for billions of years. Instead, they discovered cosmic chaos in the form of hot Jupiters. Gas giant planets the size of Jupiter or larger orbiting closer to their stars than Mercury orbits our Sun. These planetary monsters didn't just break our understanding of how solar systems form. They revealed how most planetary systems become gravitational demolition zones that destroy any possibility of life. Hot Jupiters shouldn't exist according to our models of planetary formation. Gas giants need to form far from their stars, where temperatures are cool enough for water ice to condense. This provides the solid material necessary to build planetary cores massive enough to capture thick gaseous envelopes. Yet hot Jupiters orbit their stars in scorching proximity. They complete full orbits in just days rather than years. Surface temperatures exceed 1,000 degrees Celsius. The explanation for this cosmic contradiction reveals the destructive power these planetary giants wield. Hot Jupiters didn't form in their current locations. They migrated inward from the outer parts of their solar systems through gravitational interactions that devastated everything in their path. As these gas giants spiral toward their stars, they act like cosmic bulldozers. They either eject smaller planets entirely from the system or drag them along in gravitational chaos that makes stable orbits impossible. This planetary migration process creates gravitational havoc that persists for millions of years. Computer simulations show that when a Jupiter-sized planet begins migrating toward its star, the gravitational disturbances can scatter any Earth-like worlds throughout the system. Some get flung into interstellar space. Others get pushed into highly elliptical orbits that create extreme temperature swings incompatible with life. Still others fall into their star and vaporize completely. The migration process also disrupts the delivery of water and organic compounds that Earth-like planets need to become habitable. In our solar system, Jupiter's stable outer orbit helped direct water-rich asteroids and comets toward the inner solar system. There they delivered the water that filled Earth's oceans. Hot Jupiter systems lack this beneficial delivery mechanism because their gas giant has already plowed through the regions where water-rich objects would normally form. Even planets that somehow survive the initial migration chaos face ongoing gravitational torture from their hot Jupiter neighbor. The massive planet's gravity creates tidal forces that can strip away atmospheres, destabilize orbital inclinations, and prevent the long-term climate stability that complex life requires. Any potentially habitable worlds become trapped in gravitational systems too chaotic to maintain stable conditions across the billions of years needed for life to evolve. The atmospheric effects of hot Jupiters extend beyond direct gravitational influence. These scorched gas giants develop extremely hot atmospheres that radiate intense infrared energy throughout their planetary systems. This thermal pollution can heat nearby planets beyond habitability limits. It creates additional dead zones where liquid water cannot exist. Recent studies suggest that roughly 1% of Sun-like stars host hot Jupiters. Many more show evidence of having gone through planetary migration episodes that may have ejected or destroyed their original planetary systems. The prevalence of these gravitational wrecking balls suggests that stable planetary architectures like our solar system may be far rarer than astronomers initially expected. Hot Jupiter systems also demonstrate how planetary formation can go catastrophically wrong even when all the basic ingredients for habitability are present. These systems often began with the same materials and conditions that created our solar system. But gravitational dynamics sent their evolution down a path that made life impossible rather than inevitable. We live in a solar system that somehow avoided the planetary migration catastrophes that appear to be common throughout the galaxy. A gravitational architecture stable enough to allow Earth 4.6 billion years of uninterrupted evolution. It has remained peaceful rather than chaotic. Imagine stepping outside on a beautiful day only to be instantly bombarded by radiation intense enough to give you a lethal dose within minutes. This nightmare scenario represents daily reality for any hypothetical life forms trying to survive on the countless exoplanets that lack the magnetic field protection Earth takes for granted. These magnetically naked worlds have become cosmic radiation wastelands. Stellar wind and cosmic rays strip away atmospheres and sterilize surfaces with the efficiency of a planetary-scale radiation therapy machine. The loss of magnetic protection creates a cascade of atmospheric destruction that unfolds over millions of years. Without a magnetosphere to deflect stellar wind particles, these high-energy ions slam directly into a planet's upper atmosphere. Each impact transfers energy to atmospheric molecules. It heats them enough that some achieve escape velocity and disappear into space. This process is called atmospheric sputtering. It gradually erodes even thick atmospheres until nothing remains but traces of the heaviest gases. Mars provides a tragic example of how magnetic field loss destroys habitability. Early Mars likely had a substantial atmosphere, flowing rivers, and possibly even oceans. But when Mars's internal dynamo shut down around 4 billion years ago, probably due to the planet's small size causing its interior to cool too quickly, the protective magnetic field disappeared. Over the following billions of years, solar wind stripped away most of Mars's atmosphere. This transformed it from a potentially habitable world into the frozen desert we see today. The atmospheric stripping process becomes particularly devastating for planets orbiting close to their stars. Many exoplanets discovered in recent years orbit much closer to their stars than Earth orbits the Sun. This means they experience stellar wind bombardment orders of magnitude more intense than what Earth experiences. Without magnetic protection, these worlds lose their atmospheres within millions of years rather than billions. Even planets that manage to retain some atmospheric remnants face sterilizing doses of cosmic radiation on their surfaces. Earth's magnetic field deflects roughly 99% of the high-energy particles that constantly rain down from space. Planets without magnetic protection receive the full cosmic radiation dose. This creates surface environments where DNA damage would make complex life impossible, even if other conditions were suitable. The magnetic field problem affects different types of planets in different ways, but almost always with lethal consequences for potential life. Small planets like Mars lack the internal heat necessary to maintain the molten core convection that generates magnetic fields. Large planets might maintain internal heat longer, but often develop such thick atmospheres that surface pressures become crushing. Planets orbiting red dwarf stars often become tidally locked. This can disrupt the core rotation patterns necessary for magnetic field generation. Recent atmospheric studies of exoplanets have detected exactly the kind of atmospheric loss that magnetic field absence would predict. 8D209458b, a hot Jupiter orbiting very close to its star, is losing atmosphere at a rate of roughly 10,000 tons per second. While this planet is too hot for life anyway, the observed atmospheric stripping demonstrates how stellar wind can erode planetary atmospheres when magnetic protection fails. The magnetic field requirement creates another filter that eliminates most exoplanets from habitability consideration. Generating a stable magnetic field requires a planet to maintain liquid convection in its core across billions of years. This demands exactly the right size, composition, rotation rate, and internal heat generation, a combination that appears to be cosmically rare. Even planets that initially possessed magnetic fields can lose them if internal cooling shuts down core convection. Venus likely had a magnetic field early in its history, but lost it when slow rotation failed to maintain efficient dynamo action in its core. The loss of magnetic protection contributed to Venus's atmospheric evolution into the crushing greenhouse hellscape we observe today. Computer models suggest that Earth's magnetic field has remained stable for at least 3.5 billion years. It provided uninterrupted protection during the entire period when complex life evolved. This magnetic stability depends on Earth's unique combination of size, rotation rate, core composition, and internal heat sources, a recipe that appears to be extraordinarily rare among the exoplanets discovered so far. We live under an invisible magnetic umbrella that has operated reliably for billions of years. It deflects cosmic radiation that would otherwise make our planet's surface as sterile as the Moon. Among thousands of known exoplanets, Earth's long-term magnetic field stability appears to be genuinely unique. A planetary defense system so rare it may occur only once in the observable universe.